Morning already? Taco Bell's toasted breakfast burritos will get you out of bed. With fluffy eggs, crispy bacon,
is life that
Okay, voice check, 1, 2. Hello. Welcome to the live stream lecture of new content. So I hope you've read the description. Okay, I'm just going to teach this because I need to practice before I teach it to my own students. So I'm just going to treat this like a trial run. All right, so today, hopefully people joining us, I think a lot of you guys will be sitting for your Feb March paper next week, right? That's why you are pushing us to give you the chapters. But Miss Ellie and I, our lectures haven't reached there yet because our students are sitting for the May-June series, okay? So that's why there will be no recording yet because we have to fine-tune and make sure that we teach the best that we can. So today is just like a trial run. So there will be some things that are still a bit rough on the edges and needs to be ironed out. But if you're sitting for your paper, this is new. And the questions that I'm taking from are generally from textbooks, right? So we're not quite sure how CAIE will ask the questions. So we'll just study a little bit more, make sure our knowledge are firm, and then we hope for the best. Thanks for joining me this afternoon. Okay, so Miss Ellie and I are quite flawed right now with work. So a lot of things that we would like to do for the channel, we can't, but we'll see what we can do when our schedules freeze up. All right. So, okay. So if you are watching this, this thing will be recorded as a live stream session. You can always rewatch this later. Okay. Later, when the time comes, we may actually record a formal video. All right. So talk to stuff in the chat. I'm just here for the people sitting for the paper next Thursday, guys. You guys okay? All right. So I will answer questions during the break. So the way today will go is I'm going to teach PET scans. We'll do maybe 1 or 2 questions from textbooks and also from past years. There are some questions that already hint at PET scan in past years. Okay, then we'll take a short break. So during that short break, I'll just chit chat with you and we'll just answer your questions. Okay, and then after that, we'll come back and do Astro again. All right, cool. Astro is not a very long chapter, but the whole chapter is new. So there are a lot of new things to pay attention to. Okay, so there's a 20-second, around the 20 to 25-second lag between me seeing your chat messages and me replying and you listening to me. So I also have to remember that as well. Okay. All right, so we'll begin now. All right. So medical physics, in medical physics, you learn 3 main types of medical physics. So here's my guess. Because this is new to your syllabus, okay? By new, I mean fresh new. So I'm going to guess that for medical physics, they will definitely ask you PET scan. But I don't know how many marks. I don't know. I don't know how important they'll be, but you will definitely expect a question. Unless they want to troll you. But I noticed that recently Cambridge is kind of hashtag troll. They're a bit troll. Okay. So anyway, for medical physics, there's the PET scans. There is the ultrasound, which we have already recorded, right? Because this is all syllabus stuff. Then there is X-rays and CT scan. So my guess would be they will ask 2 out of these 3. And I want to say that PET scans will definitely come up because it's new, but I also don't know. Because Cambridge can be quite troll. It's like we expect this, but then they do something different, you know, like certain people. All right, so I'm going to extend this a bit so you can see. All right. So in today's class, we're not going to talk about the first 2 because we've done them before. We're going to focus on PET scan. But before we start, I just want you to look at the names of the title of the scan. Okay, so positron emission tomography. When you say the word positron, what comes to mind here is the beta plus particle. Okay, the anti-particle of electron. Okay, emission means there will be beta plus particle emitted, and tomography is the same thing as your CT scan. It stands for the same T. So whenever you see the word tomography, this just means we have many images combined and process to make a 3D rendering. Then we can rotate, we can slice, we can look into the human body. So the whole point of medical physics is just for scanning. So your syllabus doesn't really cover the other parts of medical physics. We're focusing mainly on scanning. Like how can we look into the human body without actually cutting open the human body and injuring people unnecessarily, right? So because we involve positron, which is a beta plus particle, this is radioactive. Okay, so you might be wondering, how do we create a beta plus reaction inside the human body? Okay, so in this case, the radioactive tracer is the answer to the question. So a radioactive tracer here is a substance that consists of radioactive material attached to a natural chemical. So there are quite a few examples here. You can Google this, okay? But I'm going to talk about the most common one, which is the fluorodeoxyglucose, which is known as FDG. So I don't teach chemistry, so I just found this picture of a glucose molecule, okay? And an FDG simply means I replace one of these OH with fluorine, 18 fluorine. Okay, and the reason why I do so is so that it's like a spy. I tie so that your body looks at the molecule and your body goes like, hey, this is glucose, this is sugar, this is something that I'm used to. I'm going to absorb this in. It is a familiar chemical, but unknown to the body is that there's this little F, 18F here just hiding there, waiting. Okay, so we introduce this into the body by living tissues being studied. Normally it's done by injection, okay? And it will use to locate and follow progress of illness and treatment in living tissues. So for example, if let's say you have, I inject into this body and this fluorine 18, right? It's taken up preferentially by rapid growing cancer cells. Okay, so the thing about glucose is that your cell loves sugar, right? You don't like sugar, you like the sweet sugar snack. So your cell loves sugar. So when your cell sees glucose, and specifically when cancer cells detects glucose, it will take a lot of that glucose. Okay, so now you have different cells, but cancer cell is the one that takes all the glucose. Comment in the chat, what's your favorite glucose? Sugus, Mentos, chocolate. Okay, so and we choose FDG also because after that, we are introducing some radioactive particle into the human body. So it decays into a stable product, so it doesn't have lasting negative effect on your health. We also have a short half-life, around 2 hours. Okay, so all of it or most of it will decay within a day. All right, but the only downside of having a short half-life is that you have to prepare the sample the day of the scanning. Okay, your favorite glucose is maltose. Very nice. Is that your favorite sugary snack? Okay, Milo. Malaysians, we like our Milo. Okay, so fluorine 18 is incorporated into glucose, taken up preferentially by rapidly growing cancer cell and also your brains. Your brain likes sugar. Okay, so the main reason if they ask what is a radioactive tracer, this one is basically the definition of radioactive tracer. This is an example of radioactive tracer, your fluorodeoxyglucose, and this is why we use FDG. MSG. MSG is not a glucose, my friend. I'm not quite sure what is fructose. You like your fruits? Okay, so we have this radioactive tracer because this 18F, fluorine 18, is going to decay. Okay, and in that decay process, it will produce a positron. All right. Anyway, the link to the notes is pinned in the comment section. The printout for these notes. Okay. So positron annihilates on contact with an electron. So you just imagine there's a reaction in this 18F. Okay, and there's a whatever reaction is, it has a nucleus plus a beta plus particle or positron. This positron, right, it cannot exist. Nature will not allow it to exist for long. because there are many, many electrons in your body. And what happens when an antiparticle, positron, meets a particle, electron? They will annihilate. So this is the annihilation process. Okay, annihilation. So this happens when you have a particle, okay, in contact with an antiparticle. So this one is from your AS particle physics. The positron is the antiparticle, and the electron is the particle. And in this process, right, we are able to produce 2 gamma photons. And then you may be wondering, why must be 2 gamma photons? Why? Okay, so let me draw or write out the equation here. So this is a drawing of the reaction that is happening. Okay, we have the positron, okay, meeting an electron, and you have a lot of electrons in your body because they are part of what makes up the bonds of your hydrocarbon. So you have a positron meeting an electron, and then it annihilates, forming 2 gamma photons. But if you think about the mass number, right, this is 0 and 0. So the mass of both particles and antiparticles is converted to energy of your photon. Of course, how do we calculate that energy? We can use our Einstein E equal to delta mc squared, where this m here would be the mass of electron and positron. Okay, so you have one of these electron incoming positron, and then you have this electron incoming, and what you have is your gamma wave flying in the opposite direction. Why do we insist that they fly in the opposite direction though? This reaction is a lot like an explosion. Okay, so they are so opposite direction that, you know, they will move at 180 degrees apart. Okay, so this is because this is an explosion. Okay, if you think about your electron, right, the combined momentum of the positron and electron is 0. Because when they encounter each other, they sort of move quite slowly. Okay, so they move quite slowly, and the momentum is essentially close to 0 or 0. So these 2 gamma photons that is released must have momentum, and they will travel in the opposite direction to conserve momentum. So let us write that down onto our chemical equation. So here to here, what we have is the sum of your initial momentum. By conservation of momentum, it must be the same as the sum of the final momentum. And the sum of the initial and the final momentum must be 0, because the electron and the positron itself, during the reaction when it's created, it's not really having any speed. Okay? And in this annihilation event, as mentioned just now, the mass of the positron and electrons are converted to energy of gamma photons. Okay? So this is where our energy of photon here is this calculated using the mass defect equation. E is equal to delta mc squared. All right. So what have we learned so far? Before we can start the scanning, we need to introduce a radioactive tracer into your body. And the way we create a radioactive tracer is to substitute one of these OH. Basically, we take a compound that your body is very familiar with, and then we replace it with a radioactive element. Your body cannot tell the difference, will absorb. Cancer cell cannot tell the difference, will absorb. And cancer cell will absorb more than usual because cancer cells are rapid growing. They grow very fast, they multiply very fast, they need more glucose. This is why in PET scan, the cancer cells will glow like Christmas tree. Very bright, okay? And Why we care about this 18F is because all particles or all radioactive particles that we introduce must emit positron. The name positron emission tomography. So when we emit positron, the positron will go and find another electron that is very nearby. Is literally the positron comes out, the electron reacts, done. It's done. Okay. So during this reaction, the mass of the positron and the electron becomes energy. And because you want momentum to conserve, they have to pew, fly in the opposite direction. It's like explosion, fireworks. You must have them moving in opposite direction so that the momentum is conserved. Now, strangely, CAIE has actually asked this question in past year before. Let us look at the question. Okay. So this one is from May-June 20, paper 4.1, where they focus on the annihilation event. Okay, so let's read the question together. No context, but we read. An electron at rest has a mass of ME and a charge of negative Q. Okay, so we have electron. And it says here that positron is a particle at rest, has a mass of ME and a charge of positive Q. All right. The positron interacts with the electron. Okay, interact, I write a plus here. Electron and positron may be considered to be at rest. So before the interaction happened, we can consider that they don't have any momentum because they are not moving. The outcome of this interaction is that the electron and the positron becomes 2 gamma ray. Okay, if they say 2 gamma ray, I'm going to oblige them and write 2 gamma. Each having the same energy. So identical gamma rays. Calculate for one of the gamma ray photons, the photon energy in joule, and later on, the momentum. Okay, so the main idea we had was all of the mass of the electron and positron is converted to photon energy. So I'm going to use the equation E is equal to delta mc squared. And this will be 2 multiplied by mass of the electron, mass of the electron. So during this annihilation process, right, the gamma just comes out of nowhere. Like you imagine 2 particles, right? They meet, then suddenly there's a bright flash of gamma photon traveling in the opposite direction at the speed of light. No more. The particle is missing. So if you meet your antiparticle, if Miss Lee meets anti-Miss Lee, when we interact, we will create a lot of energy suddenly in the opposite direction, and then both of us don't exist anymore. Gone. That is annihilation. In the term English, to annihilate someone is to destroy totally. That's what annihilation means in English lah. Okay, anyway, we're going to put ME here because we got 2. Okay, we got the positron. And the electron got 2. Okay, and then we have the speed of light, 3 times 10 to the power of 8. I guess I'm just going to put this on a c squared first. This energy of photon, right? This is 2 gamma photons. This one here is 2 gamma photons. And they want one of the photons. So this one will be E over 2. So this one is for 1 photon. We will just divide by 2. But no, actually 2 to 1. No need to divide by 2. Anyway, we can find the energy of 2 photons first lah. Okay, so this is 2 photons. So I'll substitute the mass of the electron, 9.11 times 10 to the power negative 31, 3 times 10 to the power of 8 square. So hopefully this calculation is not new to you. I mean, bring out my friend in case you the calculator. 9.11 negative 41 divided by... So all of the mass is gone. All of it. The electrons and the positron doesn't exist anymore. Where's my square? So I got 1.6398, 1.64 times 10 to the power of negative 13. So this is for 2 photons. So you can then say, hence, for 1 gamma photon, we'll take this number, divide by 2. That would give us, let's go down a bit, 8.2 times 10 to the power of negative 14, or 8.19. Thank you, Kasim. So sometimes they're a bit sneaky that way. They will ask for 1 photon, sometimes they'll ask for 2. So don't be fooled by them. Always check in and try to figure out which version they want. Okay, so you can write 8.19 or 8.2 times 10 to the power of negative 14 joule. And maybe you can humor me a bit. We are also going to convert this to mega evolt. Or rather, I want to convert this to mega evolt. So if you remember how to convert this to mega evolt, which I'm going to use a different color, write this here. Our E was 8.2 times 10 to the power of negative 14. To convert this to evolt, I will divide by the electronic charge. Okay, so I have this 8.199. I think 8.2 is better, because if you put 8.19, you're not rounding it correctly. Okay, so 8.2. Anyway, I'm just going to divide this by 1.6 times 10 to the power of negative 19. And I have this, which I'm going to use the ENG button. And I find that this is 512 times 10 to the power of 3 kilo evolt. So I'll write that down. 512 kilo evolt. So in other words, right, my reaction actually looks like this. E plus plus E minus become 2 gamma, and in the process, 512 kilo evolt of energy of the photon. This one is for each photon, each gamma photon. Okay, so you could times 2 like if you want to, or just don't include it in your equation. Okay. So to find momentum, we are going to use the equations that we already learned in quantum physics. You know, like momentum is Planck's constant over lambda. And also at the same time, energy of photon is equal to hc over lambda. So what do we have? We definitely have energy of photon. We have h, we have c. Okay, so we can find lambda. Or I can rearrange this, and lambda is equal to hc over E, where E is the energy of photon. Okay, and what I'll do is I'll substitute. So hence, momentum is equal to hc over hc over h over hc over E. To make sure that they are the same size. I draw bigger for the friends at home. Nah. Alright, so what I did was I substituted the lambda, and this is my lambda. Okay, so from here the h and cancel, and I'll get P is equal to 1 over C over E, which is the same as E over C. Okay, so continue up here. Momentum is E over C. Do I have E? Yes, 8.2 times 10 to the power of negative 14. cause 1 photon. And this will be 3 times 10 to the power of 8. This will give me 2.7, I think, times 10 to the power of negative 22. So this question is not really testing the positron emission tomography. It's just focusing on the positron annihilation event. We are studying what happens during the interaction of a positron and an electron. We have gamma photons, each with this amount of energy and this amount of momentum. So if let's say I go back and I draw this out, okay, so I will have a positron and an electron, and then when they interact, what I have is some gamma. This is 512 kilo eVolt. I can easily find lambda if I want to, because I have the energy of the photon. So this is 1 gamma photon, because hey, gamma ray is also a particle, right? Light is a particle. That's what you learn in your quantum physics, what? And this gamma will be 512 kilo eVolt. Right? We care a lot about this reaction because this reaction starts the scanning process. But part B, you are asked to state and explain the direction, this direction, relative to each other in which the gamma ray photons are emitted. Okay, so we have to explain the direction. So I'll start first with the initial momentum. You can say that the total initial momentum is 0. Total initial momentum of both positrons and electrons is 0. All right? Because they also sort of mention it here, that considered to be at rest. So this one is how you know that the momentum is 0. Initial. Total momentum. Okay. So after the reaction or after the annihilation, let's use the word annihilation, new word. Okay. So after the annihilation event, what happens? To conserve momentum, both gamma photons must travel in the opposite direction. Such that the total final momentum is 0. Is also 0. So the point here is we need this to happen. We need them to fly in the opposite direction, like this. If not, the momentum is not conserved. Okay. What causes the interaction? Why do they annihilate? This kind of particle physics question. Hopefully you will learn it in uni. Quantum is weird, man. 0.5 MeV. Yep. Can. Try to leave your answers in 2 SF, okay? Don't put 1 SF. For any kind of calculation involving particles. Is it necessary to multiply by 2? I multiply by 2 here to show that it is 2 photons. But later on, I mean 2 electrons, or rather, this 2 here is to show beta plus and beta minus. Got 2. I divide by 2 here is because I have 2 alpha. Why do I keep calling this alpha? 2 gamma photons. And the reason why I do that is in case they ask for 2 gamma ray photons. Or they could ask, calculate the energy released by the interaction. Then you have to multiply by 2. Calculate the energy total energy released, then you have to multiply by 2. So I am always thinking a little bit ahead in case they throw. Yes, they are opposite to conserve momentum. That's the whole point. You need them to fly in the opposite direction. Okay. So to give you an image or an idea of how this happens, we're now going to look at how we use it in the PET scanning. That will be the next part that we'll move on to. But this is a past year question. They are like preparing you for new syllabus stuff. All right. So that's it for this one. So the important thing to understand is in this reaction, annihilation, we got positron from the fluorodeoxyglucose or any kind of radioactive tracer. This one happens inside the radioactive trace, inside the human body. So inside human. This E plus is from the radioactive tracer to trace the anomalous growth cell. Okay. It's generally if someone has cancer, right, we will send them for PET scan frequently to monitor to see if the chemotherapy is working. Okay. So I just want to show you how PET scans can look like if, let's say, you have cancer. I go Google. I ask you Google because I also Google. Okay. So let's say you are looking at, this one is a prostate cancer. You know where is prostate or not? Prostate is here. So the prostate cancer has already metastasized and spread to this part of the body. So you can tell the places that glow are the places where the positrons are gathering and doing annihilation. So a lot of annihilation process is happening here. That 512 kilo eV energy is being picked up at this part of the body. This is the kidneys. This is the bladder. Of course, your body at the end of the day will throw out the waste product and filter it through your kidneys. So we always expect to be able to see some radioactive tracing in the bladder, but this is very anomalous. Why? What is going on here in the human body? And also what is going on here in this part and this part? So if let's say I send this patient or we send this patient for chemotherapy or radioactive therapy or whatever kind of therapy to stop the growth of the cancer, this area should noticeably begin to shrink. That's why we tend to use this tracer not just to detect cancer, but also sort of to see the progress of the illness and treatment. That's why we use a radioactive cell. They detect more of the gamma radiation. It means that there's more glucose present at that place, more than normal. All right. So let's look at the PET scan. Okay. So this is how it works. Okay. So I will first introduce a radioactive tracer into the patient's body. And newsflash, this tracer can design specially for the kind of cancer and the type of tissue that the cancer cells is in. So not all will use fluorodeoxy, the FDG tracer. They can use other types of tracer. We don't need to know the other types because that's not part of the syllabus, but we can custom design the radioactive tracer just for this patient, just for their type of cancer. Okay, so once we create this radioactive tracer in the lab, we're going to inject this into a human body. And then let's say this one is to scan for brain cancer. So the brain cell, the brain tissues, and then the certain cancer cells will absorb more of this radioactive tracer than the healthy cells. And then we have a ring of gamma ray detectors here. Okay, so your positron, they emit energy in both directions. So inside this tracer, the tracer will give you a positron once it is inside the human body. That positron will find the electron to annihilate. And in the annihilation process, release 2 gamma photons in the opposite direction. So if let's say this is the patient, and we release 2 gamma photons, and then I notice that this tracer got ping. This detector got ping. So if I ping these 2 detectors, then I can draw a straight line between the detector and say that any point along this line could be my radioactive source or my cancer cell. Teacher, this feels like a very large surface. How do I know which part it is? Well, good news. We don't ping one time, right? It's impossible to have one positron. We're going to have millions and millions of this reaction. So there'll be multiple pings. So let's say someone here pings again. This one is detected. This one is detected. So they will slowly draw the line, and the intersection tells you where the cancer cell is. Okay? This interaction tells you where the cancer cell is. They call it a tracer because it traces. It's like you are following, you are trying to pick up the places where the tracer is going. Can we drink? Let me ask. Yes, it can be swallowed, inhaled, or injected, depending on which part of the body is being examined. Very cool. So you could drink it. I'm guessing you would drink it if, let's say, something is wrong with your digestive tract, maybe cancer of the stomach or cancer of the colon cancer. I would say that maybe inhaling would be something that has to do with your respiratory system, your lungs. And injection normally is your circulatory system, your blood, your lymph node, your pituitary glands, maybe your brains. But yes, you just need to put the tracer into your body. But yes, some people ingest it. It's safe to drink, it's fine. It's not poison, it's just radioactive. So it's the same idea lah. They just put different pictures so you can see. So the whole idea is wherever it is in your body, okay, when the reactions start happening, let's say for example, I have, knock on wood, a cancer cell on my shoulder here. So all the annihilation process means that I will shoot out gamma ray in opposite direction all the time from this place, all the time. And then because I am lying inside a ring of detector, the detector can draw straight lines to try to identify where my tumor is or where that high ping area is. So let's say another annihilation ping here and ping here. So they'll draw a straight line here. And then after that, another ping here and here. Then they will draw a straight line here. So after drawing multiple straight lines, we can zero into the source of the cancer cell. Yeah, it's not dangerous. It's not, we would like you to not expose yourself, but every PET scan, the radiation is around the same dose as a 8-hour flight. Do you fly before COVID-19? You fly for 8 hours? So when you fly, you will have more around the same radiation as a PET scan. So it'll be fine. All right. So now we are also anticipating an essay question. Because, you know, CAIE likes to ask you those 6-mark, 5-mark. Explain the working principle of the CT scan and the ultrasound and the production of the ultrasound and using ultrasound for diagnostic purposes. And because we don't have mark schemes or questions, I'm just going to write out an essay to describe the working principle, and we'll see how I may modify from there based on whatever question comes out this year. Okay. But here's the working principle. So I've typed out everything. Normally what I'll do is I will just, fill in the blanks with all the keywords. But this is the full text to save time. Okay, so the working principle here is, number one, we always start with the beginning of the story. So I find it easier to write these kind of essays by imagining I'm a patient and I'm about to go for a PET scan. So what's the first thing that doctor going to do to me? The doctor is going to inject radioactive tracer into the human body, or swallowed or introduced, if you want to be very general, introduced into the human body. Yeah. Okay. And the traces is taken up preferentially by cancer cells or any kind of active tissue that I want to scan. All right, any kind of active tissue that I like, that I've taken a liking to, I want to scan. This is the kind of tissue that, so basically we can actually custom design the PET scan to fit what we are looking for. And I managed to find, let me see if I can find the GIF. There we go. This is a PET scan. So if you look at, if you look at the human, the brain is bright because brain will take up sugar a lot. When you study physics really hard at 2 a.m., you watch our videos and suddenly you feel very hungry, you go and eat because the brain uses up all the sugar to learn the big brain physics, the same idea, okay? So your brain will definitely glow. I don't know if you noticed, right? Number one, this part here is the colorectal or the rectum plus large intestine of the patient. And as you rotate, you can see that there's mutation and it has metastasized. Basically, the cancer has spread into the liver. This thing is liver shape. Liver is a shape of like a triangle, right? So you can tell from this patient that it has gone to the liver. And then this part is the large intestine width. This is the bladder, because whatever you ingest into your body, it will accumulate inside your bladder. Normal one is your digestive system. Okay, so that is a PET scan. So this FDG is taken up preferentially by cancer cell or any active tissue that we are scanning for. We can custom design based on what tissue we want to detect, but that's not part of the syllabus. So for example, this one I'm actually detecting for this kind of cancer cells. All right. So this cancer cell, they like sugar because they're growing very fast. So they will eat up all the tracer. Okay. So if they eat up all the tracer will begin to decay to produce a positron. And this positron doesn't stay a positron for long at all. Almost immediately, the positron will annihilate with the electron in the tissue. Our bodies are filled with electrons, okay? Producing high energy gamma photons traveling in the opposite direction. So this is the annihilation event that we did some calculation just now. All right. So I start from the top. We send tracer into the body. The tracer is being taken up or absorbed by the tissue that we are trying to study. The tracer will decay to produce a positron. Positron will annihilate with the electron, and you have two gamma photons moving in the opposite direction. Now let's talk about the scanning. So here is annihilation. This part here is about the tracer. And here onwards is about the scanning. Okay, so when we scan this high energy, or rather we want to detect this high energy gamma photon, because gamma penetrates the body easily. So if you think about the properties of your alpha, gamma, beta, your gamma, right, can shoot out very fast. It penetrates. You need like a few meters of lead. Remember this? Few meters of concrete wall to block gamma. So this gamma photon look at your body, go like, I can penetrate body easily. Okay, so we have a PET scan of circular ring detectors. Okay, and these circular ring detectors will detect both gamma rays simultaneously. They should arrive at both sides at the same time or close to the same time. Okay, this is called coincidence detection. So it happens at the same time, coincidence. Okay, and we allow a window of 5 to 10 nanoseconds. Teacher, this means the computer that picks up the ping must have very low latency or low lag. You are correct. Right now, you watch this live stream. The latency is 20 seconds, 20 to 25 seconds. So whatever happened here takes 20 seconds to happen in front of YouTube. That kind of latency cannot use at all for this scanning. Just throw it away. All right. We need the latency or the lag time. We play game, the lag time to be 5 to 10 nanoseconds. So if you use Discord and you go to a voice channel, you will see that there is a ping rate. So we need this to be very high. So like all things, this can only be done because we have the computing power. Don't have, then cannot already. All right. So right now, when we have this coincidence detection, okay, we can say that the line between two simultaneously activated gamma detector is known as the line of response. All right. So generally, what we're looking at is something like this. Okay, is this hello? Why not a bit laggy whenever I paste stuff? Okay. So if you look at this picture of my patient, okay, so coincidence is when there's one annihilation. And to draw the line of response, we'll just draw a line between the two detector that is being pinged or being activated. So this is your activated detector. And this straight line that we draw, this is your line of response. They should arrive at the same time or within 5 to 10 nanosecond apart. Okay, gamma photons that do not arrive in pairs, we ignore. Their background radiation is just random stuff. Maybe it's some scattering, okay? Maybe there's, sometimes we reject lah. We don't care. Okay, so sometimes the reason why we have all these do not arrive in pairs, I scared they ask why, so I went and did a bit of research. This is normally due to scattering. Maybe on the way out, the gamma photon interacted with another particle in your body and changed direction. You don't know. Intercept, don't know. So this one can be due to scattering or just random, due to the random nature of these interactions. That's why we need many, many repeated interactions. Okay. All right. So we're going to have other simultaneous detection made in different angles. So let's say now we ping in this direction, as mentioned just now. Then after a while, there's another simultaneous detection here and here, for example. So here is the intersection point, okay? So the position of the source is at the intersection of the two lines of response. So what we are looking for is the radioactive source, which is, by the way, the tumor or the tissue that absorbs your radioactive element. So this cancer cell that absorbs all the tracer is the source of your reaction, and we want to find it. So imagine this part is actually here. We ping on the opposite direction, we draw a line, ping on the opposite direction, draw another line. The computer can accurately tell the position after multiple pings or multiple activation of the ring detectors. Okay? So combination of many images from various different angles can be combined to form a 3D image using a computer lah. Obviously, some hardcore coding is needed. This is like 3D printing. It's pretty similar. Okay, we are doing it one layer at a time, like 3D printing. So I think the important thing that you should mention in the scanning is, besides the tracer and the annihilation, is that you have PET scanner of circular ring detectors. Talk about the setup. Okay. Then the second thing that you should talk about is the coincidence detection. So you will say we want to detect two activated gamma detectors at the same time. Okay. And then after that, you say the position of the source or the tumor is at the intersection between the two lines. These are the key things that you should mention. So in a nutshell, if you want to tell the story, you will say, hello, human. I would like to scan to look at certain tissues in your body. I custom designed a tracer and put it inside your body. So a custom design or radioactive tracer is introduced into the human body. Okay. the radioactive tracer would decay to form a positron. Positron will annihilate with the electron to form high energy gamma photons traveling in the opposite direction. All right. And because these high energy gamma photons can penetrate the body easily, when we put the body inside a ring-shaped circular detector, like the one behind my head, what will happen is they will have simultaneous detection or coincidence detection. So we will ping both the green one at the same time, and we'll ping both purple one at the same time. And we draw a line between the detectors that are being pinged. Okay? So the position of the tumor is the intersection between two lines. So there's probably some coordinate geometry and some coding happening here, but we just need to know simultaneous detection, draw a line. Simultaneous detection, draw a line. So where they intersect is probably where the source is. And we will ignore things that don't arrive in pair. And we combine many of these images to form this one, 3D rotating drawing of a liver cancer in a patient. So this kind cannot operate one, you know why? What are you going to operate? It's everywhere. So what we'll do is we'll probably introduce chemotherapy, hoping that that will shrink the cancer cell. That is normally the course of action. Okay, so that's it for the PET scan. All right, so I feel that the questions will be fairly like the explain type, but we're going to see if we can try out the one in the, someone mentioned in the chat just now, the, what paper? Specimen paper, yes. Oh, look, here's a specimen paper question. Okay, let's do it together. So it's very fact heavy, fact based. Specimen paper can be found in the Cambridge website. Brain only uses glucose as respiratory substrate. Wow, I learned something today, Kasi. Brain only uses glucose, nothing else. Fat, protein. All right, interesting. I took bio until high school, and I'm like, okay, that's enough for bio. I cannot memorize to save my life, so we'll stop there. But then I have to teach medical physics. Jokes on me. All right, let's look at this one. Positron emission tomography makes use of a tracer containing a radioactive material that decays by positron emission. State what is meant by a tracer. Well, my friend, what is a tracer? Number one, it is a substance that is introduced into the body, right? So it's a substance introduced into the human body. I guess can introduce it into any living tissue lah. So it could also be an animal if let's say the animal has cancer, and absorbed by the tissue being studied. Okay. So it's used to trace. They're not asking you what is meant by radioactive, just the idea of tracer. So the idea of a tracer is something that is introduced into the body and it's being absorbed by the tissue that you want to study. It can be your brain tissue. So I guess since brain only takes glucose, so I guess that's the thing. That's the thing that we will inject in if we are looking at your brain. Anyway, state the name of the particles that are emitted from the body. What is emitted from the body and detected by the detectors during the PET scan, PET scan, detected by the ring detectors? Tell me in the chat, what do you think? The ring detectors. I'll go and find the paper link for people in chat, but let me know. Ring detectors, where? What does the ring detector detect? Gamma, yes. So they say particle, right? So if I want to be a bit more specific, if I see the word particles, I will say gamma photons. Very good. Well done. Gamma. Good news to you. If you are sitting for new stuff in the syllabus for the first time, Cambridge will normally ask it at like pretty basic level. Like, to warm up the syllabus kind of thing. Okay, so try not to use the word rays because we are treating this gamma like a particle or a photon. Okay, let me go and find the specimen paper. In the meantime, you can think about what to write in part B. Explain how the particles in A2, which is gamma photons, are created from positrons. How did we make those gamma appear? From where? How? What's the interaction? Got name or not? It's a bit raining today. Okay, anyway, here's the link to all the sample paper, specimen paper. Okay, annihilation with electron. Yes. For 3 marks. What else will you write besides annihilation with electron? Which is correct, by the way. So I think I'll write that down. I would say that the positron emitted by the tracer interacts with the electrons in the tissue. Is that all? What else should I write? I should talk about the condition for annihilation, right? Because basically they're asking us, explain how the particles are created. So we are actually asked to explain the annihilation process. So I explain a bit and I will say, since positron is the anti-particle of electrons, annihilation occurs. But this annihilation is what? Converting all the mass of both particles into energy. That mass energy conversion is Einstein's idea. My man, big brain Einstein. So 1 mark each. 1, 1, 1. Mass, we can say mass of the matter. In this case, the matter here is electron and positron. Yeah, all mass to photon. Correct. All right. So they didn't talk about the conservation of momentum here because they just asked us how the particles in A2, which is gamma, how did gamma exist? That's all. They did not really ask us to explain what happens to gamma after they exist. But of course, you can just write it in there. It's no harm done. But here are the 3 marks. Okay. So part C. positron can be artificially created by a process in the lab that is the reverse of the process in B. Okay. What's the process in B? Oh, this one. Okay, sure. This process creates both a positron and electron moving at the same speed in opposite direction. Very cute. So in the lab, 2 gamma can reverse and have this positron and electron. Okay, sure. Moving in the same speed in opposite direction. Suggest why 2 of the particles in A2, basically I need 2 gammas, are needed to create 1 positron. Why do we need 2 here so that I can have 1 positron here? So this is where we talk about the conservation of momentum. Okay. So I talk about the initial momentum first. So the initial momentum or rather I can say maybe the combined momentum. Combined momentum of the electrons and positron is 0. How do I know? Because both positron and electron moving in the same speed in opposite direction. You don't have to explain. I'll explain it in the bracket. Since E plus and E minus moving at same speed in opposite direction. So if the final momentum here is 0, if I only have 1 gamma, can 1 gamma have 0 momentum? Cannot, right? In order for me to, because you can say, well, gamma, can gamma be stationary? Gamma always travels at the speed of light. It is never stationary. Okay, so think about the momentum of gamma. Momentum of gamma. P is equal to h over lambda. So as long as gamma has a wavelength, which it must because it's an electromagnetic wave, it will always have momentum. So if I want the final momentum to be 0, I want PF to be 0, one person cannot cancel out with itself. So I must always have 2 gamma, then maybe they're traveling in opposite direction and they cancel out. So this is the second part. Since gamma photons have momentum and the initial momentum must be 0. Must also be 0. To conserve momentum, there must be 2. To travel in completely opposite direction. So we kind of expect explain question, but from different parts of either the tracer or the annihilation process, which is what this question is focused on. Annihilation or the scanning process. So things like coincidence detection, the idea of tomography, the 3D rendering, line of response. So we expect them to ask either certain details in this part of the question, or I guess they could ask you to calculate, like that May, June 20 paper. Okay. So I went on to the textbook and found some questions. They are pretty standard, I guess. So I'm going to share them with you, but give me a sec. This is from Oxford Uni. I hope I don't get copyright strike. Copyright strike, I see it. Okay, this is from Oxford Uni. And it's just a textbook lah, okay. So I chose this because the question looks different. That's it. It's just different question. Okay, so I'm not going to do all because I need to do astro today, hopefully. So I'll do question 3, the one with my man in the ring detector. Because there's some calculation here that is not complicated, but maybe needs a bit of practice. Okay, so the link to the question is in the chat, and I'll do question 3. This is from Oxford University Press. Wow, Oxford. Okay, very big. Let me adjust the size. All right, so the questions are not hard. It's just standard lah. They'll ask for certain facts, and then you recall them and you explain. So let's look at 3A part 1 to create space, but make sure it's big so you can see. Okay, bye. State the type of radiation used to form an image in the PET scanner. Gamma photon. Gamma photon. Okay. Part 2. State the type of substance used to produce the above radiation and describe how the above radiation is produced. So the substance that we use is called a radioactive tracer. Okay, how the radiation is produced is by positron, annihilation. Because they never give me marks, so I'm just going to write basic stuff, okay? But of course, if more marks are given, I will expand with more details. So the whole idea is we have positron annihilation with electron producing gamma photons. I think we have written this at least 3 times today. So I hope you get the idea. This is the starting of your PET scan and it's important. Okay, B. In a PET scanner, detectors are arranged radially and equally spaced along a ring. The detectors are linked to a computer which registers any 2 detectors that are each triggered by radiation in the same short time interval, your coincidence time window. Okay, the diagram represents the ring detector when 2 detectors X and Y have been triggered in the same time interval. Okay, I see what you did there. We trigger or we ping X and Y at the same time. A bit strange, the angle, but it's fine. So let me continue the question. I did not crop the second part of the question. So this is the next part. Describe how the radiation from the substance in a patient undergoing PET scan could have triggered 2 detectors within the same short time. How can we trigger 2 detectors at the same short time? Well, number 1, there are 2 gamma photons traveling in opposite direction. And the last time I checked, gamma photons, they are really fast, speed of light. Traveling in opposite direction at the speed of light. Very fast, 3 times 10 to the power of 8 meter per second fast. Okay, next part. The ring has a diameter of 2.4 meter. The arc XY subtends an angle of 135 degrees at the center of the ring. Use this information to determine the distance along a straight line from X to Y. All right, let's go back to the diagram. I want to be able to find the distance from X to Y. Maybe I'll draw a line. So X to Y is here. And I was told by the question that the arc XY, now arc XY is this one, subtends an angle of 135 degrees. So I guess if I were to, let's say his head looks like in the center, right? To me, the head looks like it's in the center. So here to here, head, 135 degrees. All right. We know the diameter is 2.4 meter. This feels like a maths question. Find the distance xy, or the length of the orange line. So let me draw this again. I have xy like this. And xy is at the circumference of the ring detector. So here is 2.4 meter, and this length is 2.4 meter, and this angle is 135 degrees. Of course, inside your brain, if you think cosine rule, I'm like, okay, I can see why you want a cosine, but I'm a bit lazy. So I'm just going to draw a line here, because right angle triangles, if you've watched enough of our videos, it's your best friend. You see this right angle triangle? So in the end of the day, I can use, let's say this is point O, I can find the distance of XO. Okay, I just need this angle. So to find XO, I will take opposite of this angle. Opposite is this one, divided by hypotenuse. So XO will be XO over 2.4, opposite over hypotenuse, sine. Sine 135 divided by 2. Okay, so XO will be equal to 2.4 times sine 3 divided by 2. Give me a sec. Times 2.4. 2.21 meter. Hence, the distance xy will be 2 times 2.21. 4.42 meter. I don't really expect this to come out lah, but in case they ask any calculation regarding the ring, the line of coincidence thing is basically just basic geometry. Okay, for now. So trust your geometry, your right angle. You want to use the cosine rule, go ahead. I prefer to just cut it into half and times 2. Okay. All right. Oops. I'm going to copy this, put it in part B, then we'll move on to the next part. This is part 2. Okay. This is part 2. All right. Behind the scenes. Normally when there's like a small mistake during the recording, what happens is Miss Ellie and I will pause the recording and then do the adjustment like this. We don't see the post edit. Pause the recording and then we move and then we continue. Because technology is not always cooperative. But anyway, here we are. All right. Part 3. Explain why the source of radiation must be at a location on or close to the straight line from X to Y. Why should the source of radiation be at a location on or close to the straight line from X and Y? So I guess for this part, we can say that the gamma photons are moving in opposite direction. And because they are moving in opposite direction, the angles, right, don't write short, angle between both paths, I know my big head is blocking, 180 degree, which is a straight line. Okay, so think of this annihilation process, one in this direction, one in this direction. Here to here is 180 degree. Gamma, gamma. Part 4. Discuss what further information could be used to locate the source between X and Y. One line is not enough. We need several lines. So I will say something along the lines where we will have more simultaneous detection of gamma photons. Okay, so the intersection between the line of response, or the straight lines, is the location of the source. Responses, more than one, right? Okay, that's it for PET scan. I don't know what else they can ask you. Like there's no complicated attenuation calculation. They can't be, because gamma is so OP that when it passes through your body and you have a ring around your head this way, it doesn't attenuate that much. So there's no attenuation, there's no reflection, because gamma is very penetrative. There could be some scattering, but we can detect, we can ignore those scattering whenever we don't have simultaneous ping on opposite direction. So I think mainly it's a very fact-based medical scanning. Okay. So the printout I will throw into the chat later. Scan. That's it for PET scan. Not too complicated. So understand the role of the tracer, why annihilation is important for this process, and when we scan, what are we looking for? Simultaneous ping of two detectors, simultaneous activation or detection in the opposite direction in the ring detector. And the source will be along the line of response. Okay, that's it for PET scan. Let me look at chat. I haven't been looking at chat. Yep. Thank you. 1.2, not 2.4, because it's in this. Yeah. Oh. 2.4. So it's 1.2. You're right. Diameter is 1.2. Let's see. Good. Okay. Let's fix the working a bit. 1.2. I'm going to put this in weight. You know why I'm laughing? Because the answer given by the textbook uses 2.4. So when I check my answer, I'm right. So I moved on. But they are wrong. Okay, hang on. 1.2 sine 135 divided by 2. So this would be 1.10, and this one would be 2.20. Okay. This one is 1.2. So our triangle looks like this. Okay, this is 90, this is 67.5 degree, 1.2 radius is x. All right. It's okay. Textbook is full of problems one. If you've done some textbook question, you will notice that the textbook are also full of errors. But you're right. The radius is 1.2. Thanks for calling it out. Maybe we can email them. Now I show you lah. The answer is here. Oops. No, they use. You're like, teacher, why they write the answer that way? I don't know. So they use 2.4 meter. Hypotenuse is 2.4 meter, which is not correct. All right, now you know. Okay, lo, like that lo. Yeah, it's normal. It's very normal to have this kind of errors. So thanks for pointing it out. So when I check my answers, hey, it's the same as the textbook, so it should be correct, right? So I moved on. But the textbook was wrong. So very normal. That's why I tend, because maybe it's also new in the textbook. So yeah, they also probably didn't do their own checking. Okay lah, that's it for PET scan. I think the rest is okay. I would not use S is equal to R theta because, I mean, I can, but I don't know the S or the length of XY. So I'll just stick to the triangle. All right, so we're done with PET scan. I want to move on to Astro because I want to just sort of finish everything today. But I'll take maybe a few minutes break first. Let me set the timer. Take a break. I'll leave this PET scan here for you to stare at. Okay, we'll probably take a 10-minute break. The printout is probably not going to look nice, but I think anything that you need will be here. This. Yeah. I don't have astrophysics notes, Martin. I haven't typed them yet. So I need to teach someone first. Then we'll see, okay, then all the errors will be flushed out, like prototype. So you are my test subjects today. And then I'll fix the notes. But it will not make it in time for the Fat March paper, people. It's not gonna happen. Because day job too busy, school got too much work, teacher struggling. Yeah, man. It do be like that sometimes. Life is tough. So I'm sorry, but there is no notes for you. I don't have them either. I have to type them out. PET scans are out, but not the astrophysics yet. So yeah, very busy, like with stuff at work. So kind of like not being able to type at the moment. So we will go old school. Miss Lee will write on the spot. Paste on the spot. Astronomy, cosmology. Because it takes time to type. In between putting out the fires at work and helping students with whatever that they need help with. You know, the students in our real life. So it's going to take some time. Not going to happen so soon. So there's no notes. I'm sorry. But I know you're sitting for paper next week. So I'm doing this so I can teach you. You got something in your brain. Now I'll probably give you some questions that are, I guess, I got them from textbooks. And textbooks questions are not always the best. As you can tell just now, there was a very big error in their solution. So we'll see. We'll learn along the way. That's the nature of knowledge when it's new. We are building it up. Okay, we are going to take a 10-minute break because I need to rest my voice. I'll set the timer for 10 minutes. Then we will return. Yeah, you go and take a break. I'll play some jazz music. Hey, we are back. Let me look at the chat. Hi, Sean. You are quite famous in MCKL in my college. Heard good things about you, my friend. Ancient paper. This one is from 2000. Thanks for that contribution. I think the syllabus have changed slightly. Okay, so this is not related to the discussion that we're having today, but since we're talking about this, I want to show you the changes in the IG syllabus. Just chatting, okay? Just chatting. You know, you go on Twitch and you're like, just chatting. Okay, chat, I'm just chatting. So let me show you the IGCSE syllabus. And then I will explain to you what is going on right now. And also, you're a bit stuck in the transition phase, okay? So generally speaking, the reason why you probably find the lecture videos helpful is because it's years of experience and also being a bit aware of the changes of the syllabus and trying to respond to those changes done by teachers. Okay, so if it's new, then there is very little data for me to go with, meaning I don't really know the scope of the question, neither do I know to what extent and what would they ask. So we're just sort of like working in the blind here. And the way I tend to solve, I so-called solve this problem, is by looking at all the textbook and trying to see some common trend and then pulling it together. But that will take some time, okay? A lot of typing. Okay, so we'll see. All right, so this is the new Cambridge IGCSE syllabus. And then if you check back at the page where they gave you the themes, right? See this space physics. Yo, what space physics? I mean, I looked at it, I laughed a bit, because what on earth is space physics? But if you were to go track down and look at the learning outcome of space physics, almost, okay, there we go. So a lot of things that are in the old. So last time, right, Cambridge A levels, there's choice for you. So basically I've been doing this job for a while, but there's choices for you. So the old Cambridge syllabus is you have the core papers and then you have the electives. So you can either elective medical physics because you're interested to see how to apply physics in medical field. You could also do elective in astrophysics. You can also do an elective in engineering physics, which is electronics and electrics and electronics, which is the op-am chapters that were removed recently from your syllabus. So last time they got choice lah. Now all no choice. So I don't know. Okay, anyway. So they learn about the solar system. Okay, but here's what they also know. They know about the star, Milky Way, and the idea of the light year. So the question that Sean pasted in the chat is mainly around this part of the syllabus or the content, which is IG content. And then we talk about the age of the star, and then we'll talk about what is a galaxy. Then galaxies are made out of many billions of stars. So that content from 2000 is moved to IGCSE. That's why I need to know what's going on in the other syllabus. So we will talk about Milky Way and what is redshift and stuff like that. The CMBR is also already part of IGCSE. So there is some overlap between what we'll do today and what is in IG. But if you have a younger sibling who is doing IGCSE or O levels for the year 2023, so maybe in year 10 this year, year 10. So maybe if they have a textbook, you can just read up on the last chapter. So by the time these students who are currently in year 10 do their A levels, they'll be well and ready for this astrophysics and cosmology chapter. But teacher, I didn't do this at all. Then it's okay lah. We do what we can. Okay, but we will also try not to clutter your knowledge with too much background, and I will follow the syllabus closely. I will follow the syllabus closely. All right. Okay. So I'm looking at the chat once in a while, but not all the time. So please don't be mad if I don't, reply for a while. Well, I'll look at chat now. All right, so let's go. So when we think about science, right, we're going to now go back to, so we need to pause for a while and then think about the idea. So I'm going to talk a little bit about history and the philosophy of science, okay, to understand why the chapter is like this and also what we should focus on. So if you think about the history of science, we always start by looking at something, okay? We observe a phenomena and we start asking questions. So if you think back about the last time when you did science in high school, and I don't know whether your teacher got tell you this before, the scientific method, the idea of observing something strange and going, yeah, okay? So our ancestors have done that for a long, long time on different things that basically makes up your entire science syllabus, physics, biochem, everything, all right? So part of astronomy that we're going to study is we're going to go back down to the stage. Meaning if we look at the night sky or we look up, because where is astro, where is cosmos? Not on planet, right? So if we observe or we look, so I'm going to say looking at the night sky, we are going to try to answer two main questions in your syllabus. Are there other questions to ask and answer? Yes, not in syllabus, okay? So the first theme or the first type of answers that we want to ask is always related to length. So if you think about yourself as you learn science, right, one of the very first thing that you learn is distance and length. So you want to measure how long something is, you will learn how to measure it. This is like one of the first chapters in your O-level physics, right? Length and time. So we're going to start with length. So theme one, we are going to talk about what happens when we look at the length. And theme two, we are also going to look at time, length and time, okay? So the first thing that we will observe when we look at the star, so basically I'm just going to ask you, what are we observing? Maybe you can tell me in the chat. You look at the night sky, what do you think humans are looking at? What are we observing? Don't have to sound smart, you can just like, anything. And yes, the videos, you will see this lah when the live stream is over. You just need to pause ahead. So what are we observing when we look at the night sky? What do you think, chat? What do we observe? Nice, we observe stars. But what exactly about the stars are we observing? We are going to be able to see two things. Number one, we are going to be able to observe the brightness of the star. You look at it, wow, the star very bright. Okay, look, brightness of the star. But in physics, we don't talk about brightness, right? We talk about intensity, which is, power per unit area. The higher the intensity, the brighter the star. Yes, okay. And because this is brightness, we like to tag on the word luminous intensity. So it's just a fancy way to talk about, oh, so bright. The star is so bright. And then after a while, we notice that if the star is so bright, it means there is electromagnetic wave coming in our direction, yes? It's bright, ma. How do I know it's bright? There is wave. So I'm going to look at this thing called the color. So we don't just look at the fact, and I put color in inverted comma because it's not exactly color. We are actually looking at the wavelengths of the EM wave from stars when they arrive on Earth. And this luminous intensity, what we are looking at is power per unit area of the EM waves from stars when they arrive on Earth. So when we say we look at the star, wow, so bright, can sing song about stars, about making wishes, we are looking at how bright the star is, which is something about energy per unit area. power per unit area. And we are also looking at the color, which is the wavelength of the light. And because we are all earthbound, you, me, everything, we are tied to Earth because of the infinite gravity, because of the gravitational potential well. We can only see things when we're on Earth. So we will be able to measure how bright the star is and what is the color. Okay, so that we can answer questions like number 1, A, how far is this other star? How far? B, how big, or in other words, what is the radius or diameter of the other stars? You get the idea? So these are all ideas around length. We look at the stars, we can only see 2 things. We can see intensity, which is power over area, and we could see wavelengths, or we can measure wavelengths. But we want to take these 2 measurements to answer questions like, how far is this galaxy? They will always say that, oh, the galaxy is 500 light years away, and you go like, how do you know? Did you measure it using a ruler? No. Okay, so we'll talk about the kind of measurement that we do and how to calculate these 2. The size of the star and how far those stars are, or the galaxies are. Okay, and with that, we are also going to try to answer the last one, which is this stars moving away from us? If so, how fast? What's the motion like? So if you think about the very basic study of any new field, we want to be able to answer questions around length and length plus time. So it sort of makes sense. All right. So this whole chapter 25 is to answer how far is the star, what is the radius, how fast is the star, and finally, so this one is description. To answer, actually it's more like to describe. Description questions. And also, finally, number 3, to try to explain, try only, because these are all just theory, to try to explain the expansion of the universe. And what are the implications? What does it mean if the universe is expanding? Are we going to die? I think all of us here that is alive right now on planet Earth will die before the universe ends. Pretty confirmed, like almost with 100% certainty. Okay, so the implication is not so much on us, but just in a universe scale, what are the implications? But yeah, so we're going to look at mainly the first part, and then we'll try to look at our answers to these questions to try to explain, how do we know the universe is expanding? What are the evidence? What are the implications? Don't know. Okay, let's start. So the first thing we're going to look at, okay, I'm going to, and I'll always do this, paste in the syllabus so that you have a reference to look at. All right. So I don't want to teach too far away from the syllabus because it's not needed, especially if this thing is new. All right, and then we'll try the papers. Stars, moon. We look at bright stuff lah. We like to look at bright stuff. Our eyes are evolved to look at bright things, which means we have to be able to define that brightness. And this is the idea of standard candles. Okay, so there are a few things that we need to know, and I will write them down. Okay, and then we will refer them to the syllabus later. The first thing that you need to know in 25.1 is luminosity. Symbol that we will give this is obviously L. L, luminosity. Okay, and this luminosity is defined as the total power of the radiated of the object, power of electromagnetic radiation emitted by an object. In this case, the object is your star. Because it's astrophysics, you know. So if it's very luminous, very bright, then we can say it has more power. Unit here is obviously watt. W. Okay. All right. Number 2. Knowing the idea of luminosity is not enough, because the star is bright when we are very close to the star. But what happens when we are far away from the star? So think back to your AS syllabus. I'm going to post an image here. Okay, think back to your AS syllabus where we study the idea of intensity. Okay, so the further away you are from the star, the bigger the area the energy has to travel. Right? So you reach here, this area of energy is now spread out to a larger area, and then travel even further, spread out to an even larger area. It's a bit like if you sit far away from the teacher, you just hear the sound wave as softer. So from last time, we learned that intensity, I, is inversely proportional to 1 over r squared, where r is the distance from the light source. Okay, the bigger the r, the more area is being spread out of. So we're going to put this together into a statement. And number 2, we're going to be calling this the radiant flux intensity. Don't be too intimidated by the radiant flux. At the end of the day, it's just intensity. It is the intensity that you have always known. But the symbol that we will use here is F. Okay? And this one is just the apparent / observed brightness. So let's say we are very, very far away from a star, Proxima Centauri, that is the nearest star to us. And we are still quite far away from it. So we need to understand that the luminosity of the star, the total power, is being spread out over such a large area that by the time it reaches us on Earth, it's not going to look very bright compared to our own sun. Our own sun is always going to be the brightest. Okay? So we will say that F, or we'll define F as the radiant power per unit area. Let me zoom out a bit. Because, you know, bigger area, you will spread out that energy goodness. Okay, so we will take F is equal to luminosity over A. But hey, what area is this? If this is a bit hard to see, you can imagine the source of your wave traveling in a 3D plane in all directions. So it's a bit like the area of a sphere. Okay, so this A here is the surface area of a sphere. Because the light travels in 3-dimension radial from the star. It's going to be a circle, sphere, moving outwards. Okay, so this A is a surface. It's like any other wave source. Like a speaker, you would treat it like a sphere as well. That's why we have the inverse square law, or F will be equal to L over 4 pi d squared. Area of a sphere. All right. So let me contextualize first. D here is distance between the observer probably us on Earth, and the object or the star. Okay. Do you need to know the equation? Yep. Is it new? Oh, really? So if you remember intensity, right? Intensity is power per unit area. Intensity from AS is power over area. But now for astrophysics, they be being fancy. So instead of power, we change this to luminosity. Okay, lor, luminosity. It's the same thing, my friend. Power emitted by a star. And intensity, instead of using intensity, they use radiant flux intensity F. Wow, much fancy. Same equation. Okay, it's power per unit area, which means this unit here for F is watt per meter square. This can reach. Write the name, scare people. No lah, scientists lah. They write the name, you get scared, but actually it's just intensity, it's power per unit area, okay? So L is power, and intensity is radiant flux intensity, F. Just being fancy, you know? Now you feel smarter. Wow, smarter. So you notice that if I know F and L, I can find the distance between the observer and the star. If there's a reliable way to know the value of F and L, I can know how far the star is from me, the observer. All right. So we're going to do some calculation involving that, but let me copy this for us. All right. So number 3. To measure distances from distant galaxy, if we can measure F and we can reliably know what is L, I can calculate the distance. All right. So we're going to look at an example from a textbook. Give me a sec to crop that example. Once I don't copyright strike me, then can already. Let's look at this one. So this is an example. It says here the star Proxima Centauri. So those of you who actually do some astro in your own previous syllabus in high school, you will actually heard of this star before. It is very close to us, so Proxima. Okay, it has a known luminosity of 2.8 times 10 to the power 23 watt. So this is your L. See this watt here, unit for power. Astronomers measures the radiant flux intensity on Earth, AF. Calculate how far the star is away from us. So if you already have the equation intensity is power per unit area in your brain, then you can just replace intensity with radiant flux intensity, F, is equal to luminosity over 4 pi r, 4 pi d squared, 4 pi r squared. All right, so if you're wondering what that d is measured from here to here. So I guess I can replace this one with d. Okay, moving on. So substitute only, yeah, lor, substitute low. So I personally prefer to rearrange first because I scared press wrongly. A bit PTSD. Okay, 1.09 times 10 to the power negative 11. All right, so I'm just going to plug this into my calculator. 3.823 divided by divided by 1.09 e negative 11. Don't forget to square root. You and me alike. 4.52 times 10 to the power of 16. So D will be 4.52 times 10 to the power of 16 meters. Okay, it's quite far. It's galaxy stuff, so it's going to be far. All right. For context, I think the distance between, let's see, between Earth and Sun is around Earth and Sun, just to compare the values lah, is around 1.5 times 10 to the power of 9 meters. So this is like, I don't know, a million times further, 10 to the power of 6. 10 million times further, 10 to the power of 7. Okay, so very far lah, okay. So that's the kind of question that you expect, direct substitution and calculation. So I know what you're thinking. Teacher, in order to find D, I need to have a reliable way to get L and F. You're right. So we can measure the radiant flux intensity on Earth using this. So there's probably a telescope that I can actually measure the brightness by the time the light reaches us. It's a bit like right now, if my face is closer, okay, wait, let me change my screen. So I use dark mode a lot. You can look at the reflection of the light on my face. It dims when I bring in the dark mode. So we have actually ways to measure the brightness in the room or in where we are, because if without that, right, when people shoot movies, you would think it's very weird one. These two lovers arguing in the movie, halfway or sunset already, then the light look different. Then you will break the illusion of watching the movie. So we can measure things that arrive at Earth. But what we cannot do is go to the star, and like, yo bro, what's the total power emitted by you? And the star is like, nani? Because power here, remember, don't forget, power is energy per unit time. So you go to Proxima Centauri and say, yo, star, sorry, I ask you first, 1 second, how much energy, light energy or EM energy you emit? Okay, so flux we can measure. Luminosity, a bit harder. So the next part, we are going to look at what are different methods that astronomers use to estimate the luminosity of stars that we can probably never get to. And they're going to use this term called standard candles. Teacher, so lame lah. The candle got light, so we call this standard candle, correct? Standard stars, so standard candles. All right. So what are standard candles? Standard candle is a class. They like to call it a class, but actually it just means a group of stellar objects. Stellar objects, it just means stars. Which has known luminosity. And whose distance can be determined by measuring F on Earth, on the ground. So example of standard candles, we're going to look at the common one. There are a lot of standard candles. It is unknown whether this is part of your syllabus, because the syllabus seems to stop here. So basically they're telling you, oh, you say you don't know luminosity, don't worry. We have a group of stars that we already know the luminosity. And you go like, wait, what? How do you know that luminosity? I'm not sure whether it's in your syllabus. Certain textbooks include this, so I will include this for you also lah. So the first example of standard candles, okay, is what we call a Cepheid variable. Teacher, what is that? Let me write name first. I haven't had the chance to go and Google. You think I learned on university, man? I didn't take this course in uni. So what I learn now, I learn by Google. Google, read Wikipedia, and then read website, and then watch video. Like this is how you learn knowledge, right? So it's normal. It's normal to learn. You have to keep learning, man. You gotta level up all the time. So a Cepheid variable, hope I'm not mispronouncing it, is stars that you have radius changing periodically. Okay? So these stars, right, I'm gonna place in so you have to watch me writing. These are stars that the radius change periodically. So the stars will expand and contract and expand and contract. Okay? This causes the temperature of the star to change, so the luminosity will also vary periodically. So we sort of expect the graph of luminosity, brightness against time to look something like this. Like a candle, this star will flicker bright, to dark, to bright, to dark, to bright, to dark. Means I go outside and see the star flicker can, my friend. Unless you want to stare at the star for 5.4 days. In that case, I will salute your dedication. We can't detect the flicker or the change in brightness. So what scientists do is that they go to a very cold place that have minimal light pollution so that the data is not disrupted. They point a very sensitive telescope to the star and they measure the intensity and wait for it to drop and rise. Drop and rise, drop and rise. Okay? So every star that is inside the Cepheid variable classification demonstrates this brightness variation. Like a candle, it will flicker, bright, dark, bright, dark, bright, dark. This is not interference, right? It's just the property of the star. Okay? The gas, because star is a giant ball of gas. So whatever that is happening inside that star, it will cause it to glow and then dim, and then glow and then dim. Don't get me wrong, it's still bright. It's just that it will glow and dim across 1 to 100 days. So the luminosity will change periodically. Okay? And then the second thing we notice is that all Cepheid stars with a given period have the same luminosity. So if I can find another star that is 5.4 days, and then I compare and cross-reference, they will have the same luminosity, which kind of makes sense because that luminosity is due to a property of the sun expanding slightly and contracting slightly due to the reaction. Okay, due to the multiple reactions of the hydrogen inside the star. So if you have the same period, stands to reason that you have the same L. And a bunch of very dedicated scientists managed to plot a graph of luminosity against period. And they find that all of these stars, they fit in the trend. Okay? They fit in the trend. So from here, I can actually read the graph, I can read the graph and like, hey, let's say, for example, your period is 30 days. So I can actually read, let's say it's 10 days. If your period is 10 days, and let's say you are a type 1 Cepheid, this is your luminosity L. Can read from the scale. Okay? So what have we learned in this part? We learned this idea called standard candle. Standard candles are a group of stars that we group them together because we already know their luminosity. How do we know the luminosity? We use the idea of Cepheid variable, okay, where I noticed that the radius will change periodically. So if the star expand a bit and shrink a bit, expand a bit and shrink a bit, the luminosity or the brightness will also change periodically. So if I point a sensitive telescope and record a very, very long time lapse, I will notice that the brightness increase, decrease, increase, decrease, increase, decrease. And then I measure the period t. Once I measure this period t, I can plot a graph of luminosity against period and I add it to my data. So there are certain stars that are very close that we can measure, we can reliably measure luminosity and using this equation. So for very close stars, because you're wondering how to start the data, I need to have the graph first before I can compare, right? So for very close stars, we can measure F always. This D, we can estimate. Teacher, estimate how? Estimate using the arctangent method. Okay, it's not explicit that they will ask you this in your syllabus, but I think gravitational field they've asked once before. Maybe I'll dig out a question. But the whole idea of the arctangent method is, I'll draw here. Let's say you are here and you look at, whoops, you look at this star. And then in a known period of time t, the star has moved here. So you can use S equal r theta to actually estimate what is r. Because you know the radius, I mean, you know the orbit. So you can estimate using right angle triangles. Okay, which is a bit something like what we did in the PET scan just now. But this is the arctangent method. Okay, so we will not talk about this because it's not specified in the syllabus. Yeah. Nothing. So we have done the first one. Understand the term luminosity. Yes. Recall and use this equation. Yep. Understand an object of known luminosity. I already know the luminosity is called standard candle. Understand the use of standard candle to determine distance of galaxies, not the arctangent / light year method that is covered in your IG. So I'm only going to assume that it's not needed. Okay. So standard candles are like your Cepheid variables, this one. So if you already know the period, you can observe the dimming and the brightening, then we can estimate your L. But for very close stars, we can calculate L. L is determined using this method by estimating D. But if the stars are far away, we can't use this method anymore. You can't just like draw a very large circle and then just assume that it is that far away. Okay. Yeah. So the whole idea of this arctangent method, you can also look it up. It's also called, I have this bad habit of zooming out and not zooming in. But yeah, I got a big screen. Okay. This is also called the parallax method. Okay, not in syllabus. All right, not in syllabus. I just needed the name. Okay, so in other words, right, once we know the standard candle, the standard candle's luminosity, we can actually just use this graph to take a reading. All right, so here are some examples of known standard candles. Okay, so these are the stars that we sort of know about. Obviously, our sun is the closest. This is the distance d in terms of light years. So light years is not part of your syllabus anymore. It is in the IGCSE syllabus. We know the temperature. This one is later. We'll talk about this later. And the one I want you to focus on is this luminosity. So if I take sun as a level of 1, Sirius is 25 times brighter than the sun, and Canopus is 1,100 times brighter than the sun. Alpha Centauri is 1.5 times brighter than the sun. So all this is measured. This is the 6 brightest stars. Okay, and solar luminosity, if they want you to use, they will give it to you here like this. Okay, so we're going to look at a question, I guess. And this one is from I think it's from the publisher called Hubble. Right. I borrow the question to discuss with you lah. Okay. All right, so let's look at the question. Let me zoom out a bit. Make sure it's in scale. Okay. All right, let's go. Oops. Not something. Okay, so in this question, it says that the Cepheid variable has a period of 10 days and its radiant flux intensity, apparent brightness, as measured in the Earth orbit is 1.4 times 10 to the power negative 10 watt per meter squared. So I have F. This is F. And this is the period 10 days. Use the data from this graph to estimate for the Cepheid variable what is the luminosity and the distance from the Earth d. So to find d, I'm pretty sure that I'm going to use the F is equal to L over 4 pi v squared. Okay, that equation lah. But what I need is L. So they say use the graph, and then they say 10 days. So now I'm going to stare at the graph a bit. Use the graph and 10 days. So right now, if I go up here, 10, this is just estimate. It looks like it is half. But if you check the scale, there is something strange going on with the scale. Okay, I want to say first, I don't know if this part is in your syllabus, but I'm going to teach it as if it is, because it's extra stuff. Or not, I don't know. They say use standard candle. This is a standard candle, so I'm using it. It's the simplest standard candle. Later I'll show you another one that's not so simple. So here there is luminosity and period, okay? And then this is multiple of sun's luminosity, L sun. We're going to take the value of L sun that is given previously, okay? Both axes is logarithmic scale. And you're like, teacher, what means logarithmic scale? Okay, you look at this graph. This graph very strange, right? You see, you see. Here to here, or rather, this 10 to the power of 2 is 100. But this 10 to the power of 3 is 1,000. And this 10 to the power of 4 is 10,000. So you think to yourself, here to here 90, here to here 900, here to here 9,000, nani? So obviously this is not a linear scale, okay? It is a logarithmic scale, okay? So why do we use a logarithmic scale? Is when our numbers are either too big or too small. Examples of this, if you do chemistry, is when you calculate pH, which is the intensity of your hydrogen ion. So we're going to use a log scale. And if you wonder how the log scale looks like, if let's say we plot this out in a straight variable, let me show you how it looks like in your past year question. I don't know whether you recognize the past year question, but I think it's quite old. So this is when you encounter a log scale. This is how it actually looks like if I draw the lines. Ooh, so strange. Okay, this log scale is only on the y-axis. This graph log scale is on the y and the x-axis. You see, 1 to 10 is the same distance as 10 to 100. Nani? Cannot lah. So this and this is actually the same. In fact, I can even move it up to try to match the distance. Right? Something like that. Okay. So how to read this? Good question. So let's look at this one. This one is 10 to the power of 2. I'll talk to you about how to read the log scale. This is 10 to the power of 2. This is 10 to the power of 3, right? So what is here? And here, and here, and here. What do you think, chat? What is all of this? So if you already solved this past year question, you will know that this is 200, this is 300, 400, I'll zoom in a bit. 500, 600, 700, 800, 900, 1,000. And you're going to think like, teacher, this, how to estimate? Teacher, how to estimate? See this? Cannot estimate, right? Very hard, right? Okay. So right now, when we estimate, this is half. It's actually not exactly half. It's not. It's not half. If I take the midpoint between 10 to the power of 3 and 10 to the power of 4. Let's say I take the midpoint. 10 to the power of 3 is here. This one. And 10 to the power of 4 is here. Just this one. I hope that if this comes out in your exam, they will give you this vertical line and not give you this kind of graph. This graph is just horrible. Okay, just bad. All around bad. Okay, but it looks like it's in the middle. I'm just going to gamble that the middle is, I guess, somewhere here. Right? So somewhere in the middle. Okay. So because this is in the middle, we are actually going to have to estimate this one as 10 to the power of 3. Okay. But this one is 3.15. So it's a bit like, where is the middle? 1, 2, 3. So the middle is somewhere here. So if you are looking at this is 1,000. Okay, this is 2,000. 3,000. 1, 2, 3, 4. 4,000. So it's roughly around 3 to 4,000. It's not exactly the middle either, because I know the values. Okay. So if I change this 4,000, okay, this 4,000, because it's around 10 to the power of 3.2. No, wait. 3. I mean, it's slightly less than 4,000. So 3.25. I'm just guessing, right? So they should give you a scale, otherwise you can't read. Okay. So me doing this question, knowing that there's no obvious solution, is to show you that when you do textbook, you will get stuck, because textbook is not always the best source. Past year question is. So if you're very stubborn, I must do textbook. No, they print very nice, I cannot solve one. So in order to get the answer that is described at the back, this thing is 10 to the power of 3.15. So people in the chat, let's crowdsource solution. Do you have an accurate way to estimate this? Yeah. How do you estimate this? Because over here is 10 to the power of 3, 10 to the power of 4, but because the scale is like that, so there's no way to accurately estimate this thing. I can say it's between 4,000 to 3,000, 3 to 4,000. But I don't really know. Okay? So yeah, don't know. So I'm just going to tell you, I'll estimate this as 10 to the power of 3.15. And this would be, I guess, is it 3.15? Yeah. So my question here, I'll leave it to you, is how to read. I know you come to us for answers, but Miss Ellie and I haven't figured this part out yet. You know, let us know. Okay, so we're just trying to brain the log scale, because I don't think that there's any so number one, we don't know whether it's in the syllabus. Number two, we also don't know how they want us to estimate. Like, don't know. So I am still in the process of asking some maths teachers, and teachers are busy people, so they will take 1 or 2 weeks to get back to me. Okay, so I've already started asking people. But hey, if you know, let me know in the chat. So how to read this one? Don't know. So I'm very honest with people. So I'll tell you now that this is number one, don't know whether it's in syllabus or not. Number two, how to read, okay? So if you can read this, okay, if they give you a scale like this, then okay, you can read. This one is the best. But if they don't give you a scale and they give you a scale like this, I don't think there's a way to estimate. Although it's in the midpoint, it is not 3.5. Pretty sure it's not 3.5. So I don't know what this is. Okay, so you can let me know, because I don't know. All right. So right now, if I take this one as 10 to the power of 3.5, the ratio of the luminosity of the star divided by the ratio of the luminosity of the sun is 10 to the power of 3.15. So if you want to find the luminous intensity of the star, let me change the thickness. You will take 10 to the power of 3.15 multiplied by luminosity of the star is here, 3.83 times 10 to the power 26. Okay, I'll just write here. Given L is 3.83 times 10 to the power 26 watt. Okay. So 3.83, 26. So I got 5.4. It's not 3.15. Is it 3.25? So I got 3.4. No, 5.4 times 10 to the power 29 watt. So this is the closest version of the answer that I can get that is still within reasonable estimation. But the question here is just how to estimate this. How? Based on a graph like this. And there's no past year question for me to cross-reference on how kind of graph would they give you. The only thing I have is this very old MCQ question that looks like this from AS. So if this, I can read. So it's in the midpoint. I think it's around 3,000. But how do I read it here? Because if I put this one as 3,000, I don't get the answer at the back of the book. Although the book can very well be wrong. So don't know. Next, B. But once we can estimate the luminosity of the star, we can use the equation F is equal to L over 4 pi d squared. So we just repeat the calculation. D squared is 5.4 times 10 to the power 29 over 4 pi. We do have F. F is here. There. 1.4 times 10 to the negative 10. So please, when you do questions, this is the new syllabus pane. Without past year question, it's very hard to move forward to know the scope of the syllabus. And without past year question, we only have textbooks. And with textbooks, there's always error prone, or there are some important details that are not made obvious in your past year. So we can just play the guessing game until we try to figure out what the question wants from us. All right, that's why I didn't not do the question, because I want to show you what we are looking at right now. Okay, let's get the answer. This is 1.48 times 10 to the power of 24 meter. So the 20-minute lecture videos that you watch by Miss Ellie and me is hours and hours of work, okay? That's work that you don't see. So appreciate your teachers, not just us. I mean, a lot of time is spent for prepping. All right, anyway, twinkle, twinkle, little star. This star is very far away. So how to read this thing? I've asked a few further maths teachers. No one has gotten back to me yet, so you chill first, okay? When I know, I will record a video. I don't know yet. But currently, this is what we're dealing with, okay? Let's look at a slightly different question, where it is not that such a pain to estimate the Cepheid variable. Cepheid variable? Okay, I got this from a different textbook. I think this one is from Collins. And no time to type, so I scan. All right. So this one, it says that a type 1 Cepheid variable star observed in the Andromeda galaxy have a period of 30 days. All right, sure. The observed radiant flux intensity of the star F is given. The radiant flux intensity of the sun at the Earth is also given. So this one is F of the sun. This one is F of the star. Average distance between the Earth and the sun is this much. So this one is D of the sun. Sun and Earth. Use this information and the relationship between period and luminosity shown in figure 25.5 to estimate the distance to the Andromeda galaxy. Okay, I'm going to pull out the figure in 25.5, which is this one. Let it be BRD. Hang on. Fix it. Okay. So again, we are encountered with this linear log scale graph. Okay, it's the same thing. But the good thing here is we are looking at 30 days. 30 days is beautiful because we don't have a problem. It is right at a known value. So this is a type 1, so we're going to read from the type 1 axis. 30 days is somewhere here. And if I extrapolate, it looks like it's from 10 to the power of 4. Yay. Okay. So the L of the star divide by, you see this slash, this divide here, slash L of the sun is equal to 10 to the power of 4 because the period is 30 days for type 1. Okay, the period was 30 days for type 1. All right. So we're going to use the relationship F is equal to L over 4 pi d squared. All right, L over 4 pi d squared. And we actually have D for the sun, right? So if you look at the data that is given to you, this one here. Okay, so we have D, and then we are gonna have to use the equation once for star and Earth, and use the equation another time for sun and Earth. Okay. Ratio is my best friend. I prefer to write this in ratio format. Okay. But you can obviously use simultaneous equation. How should I place this so you can see both? So I want D. Let me rearrange. D1 over D2 square is equal to L1 over L2 multiplied by F2 over F1. So from here, if you want to rewrite this, this is D is equal to L over 4 pi F D squared. So I use ratio, okay? Should be familiar by now using this one. So when it comes to this kind of ratio, right, what I'm doing is I'm taking, okay, I'm going to make it like obvious here. Let 1 be the distance and the flux between the star and Earth. Okay, 2 between the sun and Earth. Okay, we want the distance of the galaxy from the Earth. So this is what we are looking for. We are looking for D1. Okay, so do we have the distance from the sun and the Earth? Got there here? D sun and Earth is 1.5 times 10 to the power 11. So put 1.5 times 10 to the power 11 square. Okay. L1 over L2. 1 and 2 is star over sun. We have star over sun, right? 10 to the power of 4. Then this one. This one. All right. And finally, the radiant flux of 2. 2 is the sun and Earth. Now, F sun is this one. 1.37 times 10 to the power of 3 over the 1. 1 is star and Earth. Star and Earth is 5.4 times 10 to the power negative 16. So 5.4 times 10 to the power negative 16. Phew, that's a lot of data. Yes. Astrophysics scientists are very hard and patient workers. They have to collect data across a long period of time. Okay, I'm just going to press my calculator, okay, and save you some time by not showing you what I'm pressing. Okay, I have with me. Wait, let me double check and make sure I press correctly. 37 times 10 to the power 3 divided by 5.4. So I got 2.389 times 10 to the power 22. Okay, so you can say D1 is 2.4 times 10 to the power 22 meter. Okay, so this one is probably how it should come out. I don't think they should ask you to read the log scale because it's not like an obvious thing that was emphasized in your syllabus ever. But some textbook require you to do that. And I think it's just a textbook being extra. This is just me being as extra as I think is reasonable. Not too far away from the syllabus, but not too complicated until you get stuck with the log scale and forget about the physics. So let's rewind and think about our physics. We look at the star and we're asking ourselves, how far away is the galaxy? What we can definitely measure is the radiant flux intensity, the intensity of the star by the time it reaches Earth. So F is always measurable. L is the problem. L is the problem. We don't know the luminosity. So we can have this thing called standard candles. Standard candle is standard already. The brightness is standard. So how we identify the standard candles? This is a type of standard candle, the Cepheid variable, where there's a period of flicker. That's why we use the word candle. It will bright and dim at a reliable duration of time. And because of that, if we know the period, we can read the graph that we already have. Okay? But the only problem here that remains unsolved is we may not know how to read anything that is in between these two numbers. But it was never emphasized in your syllabus nor your paper 5 on how to read or plot a log scale. So I'm not going to spend too much time doing that. I mean, I can do the hardcore maths, but I'm just wondering if there is like a fast way to do this. We'll see. Yeah. So that is your standard candles. All right. I'll briefly mention the second standard candle, but I honestly don't think that that they will ask you this because it's not linear. And when it's not linear, it is pain. I think that's not linear, it's pain. Okay, so linear is hard. Okay, so the second standard candle that we will use is the supernova. Wow. Okay, specifically type 1A. Okay, so if we have time, I will probably record a bit more about this, but I don't really think it's part of the syllabus. So the only thing I want to mention about the supernova is that we use it for galaxies that are far away, because your Cepheid variable method, the one that we just did, is only for galaxies that are close to Earth. Other standard candles include the supernova, and this is your type 1A supernova's light curve. It's looking like this. So we don't want to deal with curves. It's not good. And if let's say you want to look at something that is textbook, it's going to be like this. Okay. Well, this is in some of your textbook, but this is your type 1A supernova. And once again, it looks somewhat linear from here to here. So we can still roughly estimate the graph. We are just taking this section, this section here. Now here. But you're going to look at a flicker of 100, 200, 300 days, okay? So we need that telescope looking at the sky for a long, long time. All right, so I'm not going to do calculations involving this because I think we are quite far away from the syllabus. And if we go back to this, what they want from us is still understand the use of standard candle to determine distances to galaxies, which is what we have done just now with this graph. Okay, so so the whole idea is just there's a certain period, and from the period, I can tell what the luminosity is from previous data, from graph and from light curves. All right, so that's why we call standard candles as a group of stars that we already know the luminosity, and we can find the distance by measuring it. All right, that is 25.1. Okay, we're going to go on, and we're going to talk about this second part, which is called stellar radii. I'm going to take a 1-minute talk break so that I don't keep talking and feel that my throat is running very dry, and organize the notes. If you have any questions or comments, you can ask in the chat. No, all right, we're going to continue with stellar radii. So the first part, we learn to use L to measure distance. You see the word radii, you see the word stellar. This is just the radius of star. So the second section, we're going to look at how we can measure the radius or the size of a star. So to do that, we are going to use this Wien's displacement law, okay, to estimate the surface temperature. We're going to use two laws, basically, okay? And then we're going to use this to estimate the radius of the star. So let's talk about the laws first. Number one, Wien's displacement. Pretty sure I'm butchering his name. It's not a very good name. No, jokes. Okay. So before we talk about Wien's displacement law, I need to talk to you about black body radiation. Okay. So black body radiation is sort of like a spectrum of light that is emitted by any heated object. So I don't care what object you are using, all right? As long as you're above 0 Kelvin, so this heated object is above 0 K, there will be some form of electromagnetic radiation coming from your body. And needless to say, the sun is very bright. So we notice that looking at the light wave that comes from the sun, different intensity will have different wavelength. Okay, so here you can see that this is the graph of intensity against wavelength. So let's say the star is not that hot, 300 Kelvin. So you can see this lambda is long, okay? And then 1200 Kelvin, you can see here that the lambda is short. So I can see when the temperature increases, the wavelength decreases, which sort of makes sense because, E is hc over lambda. Lambda decreases, energy increase. So you get more energy because it's hotter. Okay, quite logical. And because of this, we know that at all temperature, radiation is a continuous range of wavelength. And the only thing that we're going to focus on is the peak of the graph. Everything else, we don't really care, okay? And we know the higher the temperature, the higher the power. So this peak of the graph is going to be known as lambda max. Okay, and lambda max depends on temperature, which brings us to our Wien's displacement law. Okay, so I'm going to write that down for us. This is Wien's displacement law. One increase, one decreases. When your wavelength increase, your temperature drops. So lambda max is inversely proportional to temperature. And lambda max here is given by the equation B over T. Because you remove the proportionality relationship, right? So this one is important, especially the equation down here. All right, you may be thinking, what is T? T is temperature, thermodynamic temperature. So if you remember from your previous chapters about thermodynamic, this is in Kelvin. Okay, and then what is B? B here, B. It is called Wien's displacement constant. Okay, so probably some experimental value that was being done. 2.898 times 10 to the power -3 MK. So this will be given to you in the exam if they want you to use calculation. But most of the time, I'm going to guess that they will want you to use it in ratio form. Ratio is your best friend. Please ratio. All right. So Wien's displacement law. Okay, I'm just going to call it number 2. Number 3, Stefan Boltzmann. When was the last time you heard the name Boltzmann? Is he from some gas law? It's like he has his name everywhere, right? Yeah, because he was alive during the time where science was fresh and new. So discovered a lot of stuff. Anyway, luminosity is proportional to temperature to the power of 4. This is Stefan Boltzmann law. Okay, so if you want to write it in a sentence, you can say for a spherical object of radius r, emitting black body radiation at thermodynamic temperature T, its luminosity is given by this equation. So proportional to T power 4, I remove the T to the power of 4, and after that I insert everything as constant. So L is equal to some constant T to the power of 4. This is 4 pi r squared, because radius of a sphere, not radius, surface area of a sphere, spherical object. But this is 4 pi r squared times sigma. Or 4 pi sigma r squared. It's the same equation. Let me double check and see which one is given to you in the syllabus. Because your syllabus is the one that decides how you will use the equation. It's also a bit like, you know, oops. Let's say, yeah. The syllabus gives you the equation, but sometimes you would prefer to write it in a different way. And I guess you would want to write it in a different way because you are more familiar in solving it in a certain way. So the way to solve this problem is either you memorize your own equation and you don't rely on the syllabus. Or if you want to rely on their list of equation, then you got to go and ask what's the equation law, which I'm going to give you now. Okay, so they will give you the Stefan Boltzmann constant. But if they want you to do this, they will have to give the Wien's displacement constant in the formula, in the question itself. So sigma is this, and the equation for Stefan Boltzmann law is also given. So the reason why I rearrange it this way It's not to confuse you. It's because this is given to you in the formula sheet in this format. Okay. But 4 pi r square here, just so you know, it's the inverse square law lah. You will see it all over one. Inverse square law. Because this is basically anything that propagates outwards, it goes in a 3D sphere. So area of sphere, 4 pi r squared. Of course, the proof is not in our syllabus, but you know, we're just going to use the equation. So we have sigma, which is the Stefan-Boltzmann constant. R is the radius of the star, which we can find, and T is your thermodynamic temperature in Kelvin. Always in Kelvin. Kelvin is the OP unit for temperature. Okay, equation given, this one given, just make sure you know how to use. All right, we're gonna do the sample paper question now. Specimen paper, because we have enough to solve it already. But I want to pause a bit and remind you, this is what we are observing when we look at the night sky. I'm going to draw a flow chart to summarize what we have done so far. The first thing that we can always measure is radiant flux intensity, F. And F was L over 4 pi d squared. So from here, I can find D. One of my inquiry here, distance of the star from observer, and most of the time observer is on Earth lah. Okay, sometimes we will observe some period of variation of intensity when it goes bright to dark to bright to dark or dim. This is where we will introduce the idea of standard candles. And from the graph, we can actually find L. And this L is something that we can then plug into this equation to find D. This is the idea of standard, and this is the one that we did just now. Okay, based on what we have uncovered just now, or based on the Stefan-Boltzmann law, we can measure lambda max of the light from stars. Okay, and we can use the Wien's displacement law which is lambda max is equal to B over T or proportional to B over T. And from here we can find temperature because we can also use the Stefan-Boltzmann law. I'm gonna include our friend here. Stefan-Boltzmann. What is his name? 1N, 2N. Law. Where L is equal to 4 pi sigma r square T to the power of 4. So this T, temperature that I can find using Wien's displacement law, will be able to help me tell what the temperature is. Okay? And then this luminosity will obviously help inform this one. Can see or not? This T can put here, L can go there. Okay? And finally, you can now find R, because what we're looking for, again, we want to measure the stellar radii, or the radius of the star. So we finally get what we want, which is the radius of star. So we are calculating either distance of the star or the size of the star. This is the overall mind map that we have right now. Okay, we look at the star, we either measure the radiant flux intensity or we stare at the period in order to give us luminosity. Once we have luminosity, we can estimate the distance, or we can plug it into Stefan-Boltzmann law, provided we have information about the surface temperature. And we know the surface temperature by Wien's displacement law. So you can plug everything in and find the radius of the star. But this is the outcome that we want. Distance and radius. Let's look at the specimen paper. Specimen paper. Line. Okay, so in this specimen paper question, ASP, we have a star with a luminosity known to be this one. So they already know, they plot the graph, they read the reading already. Okay. Scientists observe this star finds that the radiant flux intensity of light on Earth is this one. Okay, this is F. On Earth. Very nice. Name the term to describe an astronomical object with known luminosity. You already know the luminosity. I give you a hint. It ends with the word candles. Can you tell me what's the first word? You already know. You already know how bright it is. It's a bit like, hey, I already know how hard the syllabus is going to be. What do we call this? I already know how bright it is. Or rather, I already know how luminous it is. I wonder those people watching the recording of the live stream, like watching Twitch, right? So I'm going to assume that the 13 people here joined a bit later, didn't watch the first part. But if we already know, correct, thank you so much, Nazia, standard candles. Okay, what am I doing? Standard candles. Okay, look, if you already know something, means already have standard, correct? If this is not a new chapter, we already know the past year question. We know the standards, and now we don't know. So we are operating blind, as some of you mentioned just now. No past papers, so don't know the standard. Very good, well done. Determine the distance of the star from Earth. Well, we use the, F is L over 4 pi d squared. Plug and play. 2.6. You see a sneaky nano here? 10 to the power negative 9. Don't forget. L, do we have L? Yeah, L? Yes, we do. 4.8 times 10 to the power 29 over 4 pi d squared. You can show the substitution and immediately just calculate, because it's only 2 marks. So I'm not going to be too much concerned about showing the algebraic solution. So the answer that I have is 3.83 times 10 to the power of 18 meters. It should be far, far away because the nanowatt is really, 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 really small. Okay. All right. Next. The sun has a surface temperature of 5800 K. So I have T sun. The wavelength lambda max of the light for which maximum rate of emission is 500 nanometer. Okay, lambda max for sun. A scientist observing the star in A, this don't know what star, this star, a star. So the scientist observing a star in A finds the wavelength for which the maximum rate of emission that occurs from the sun, the star, is 430 nanometer. So this one is lambda max for the unknown star in A. Show that the surface temperature of the star is approximately 6700 Kelvin. Explain your reasoning. So the only thing that relates temperature and wavelength is your Wien's displacement law. So I name drop his name first lah. Its name, probably a hint. Lambda max is inversely proportional to 1 over T. So I can go like lambda of sun over lambda of star will be surface temperature of star over surface temperature of sun. So the wavelength of sun is 500 nanometer and the star is 430 nanometer. I preserve the nanometer so I can cross them out. Temperature of star, we're looking for star. But I know the temperature of the sun, which is 5800 Kelvin. So it's a matter of using ratio only. Don't worry, the calculation in this chapter is not complicated. And it's the first time. We don't expect complication. So if you cross multiply, you get 6740 Kelvin, which is approximately 6700 Kelvin. Sure. So the marks that, the place that we want to see to get mark is either this or this for C1, and then the substitution for another C1, the ratio, correct ratio substitution. Whereas for this one, you show the substitution, you get 1 mark, the distance as well. Easy. All right. Use the information in A and B1 to determine the radius of the star. So this one, we need to use our friend the Stefan Boltzmann law. Stefan Boltzmann, L is 4 pi sigma r square T4. Copy from front page. Okay. Given that sigma is 5.67 times 10 to the power negative 8 watt meter negative square K negative 4. So this both of these can find from your formula page, okay? So go to your formula page and find the answer. Boleh cari, can find from formula page. Okay, let's substitute. Do we have L? That the luminosity of the star is 4.8 times 10 to the power 29. This Stefan Boltzmann law, right, is basically just saying the brighter the star, the hotter the star. Makes sense, I guess. Sigma is 5.67 times 10 to the power negative 8. R squared, we're looking for R. Temperature. Even if you can't prove, please use back the value that is given to you. It's up to you whether you want to use 6700 or 6740. I will use 6700. As long as you show your substitution, you'll be fine. 9 4.67 negative 8 6700 power 4 8 square root answer. All right, I got my R as 1.828. So 1.83 times 10 to the power of 10. 1.8 times 10 to the power of 10. 2SF is good enough. That's it for your past year. I mean, specimen paper. Oops. Specimen paper. All right. So I don't expect this part to be hard because it's just both the Wien's displacement law, where your lambda is inversely proportional to temperature, and then being able to find the radius using the equation that is given. Since both of this equation is given, this equation and this equation is given in the formula page. What I'm more concerned about is the idea of standard candle, because the syllabus was very vague, no standard when it comes to standard candle. So cute, okay? So hopefully it's not too complicated. You can either read it directly from the scale, or they'll just tell you lah. They'll just tell you what the luminosity is, like in this sample paper question. So once you have the known luminosity, everything else is very easy to solve. Think about this. Once I know L, once I know this L, everything else I can find. Okay, so it's just, yeah. All right, the last part, very last part. We're in the home run stretch. I not focus. Coba mati ya. I clicked away. $25.3. Okay, so new syllabus, new stuff. Always refer back to the syllabus. We have done. You see, when your syllabus say recall, means you need to remember the relationship. So equation not given. That's what recall means. Recall. If they say use, that means equation given most of the time. But we have done these two laws, and then we have used to estimate the radius of the star. That is the spirit of the specimen paper question. All right, we're gonna move on to the last part, which is Big Bang Theory. Oh, fun, fun, fun. Okay, so this one, we need to review certain things that we may or may not remember from our previous chapters, starting with the line emission spectra. Okay, and then we need to talk about the Doppler effect. Okay, so let me just roughly remind you what is the line emission spectra, and thing that you have studied before not too long ago in quantum physics. So recall, line emission spectra is the absorption spectra, and we know the sun is very hot. So you imagine that there is a hot sun, a very hot sun, and that sun, white light will pass through the cooler outer area. So if let's say this is my sun, hang on, let me draw. This is my sun, and the sun is just a ball of gas, So inside here is hot. And then you have white light shining out. Try to draw. So you have the white light going out, white light going out. I know this is not white, but I don't really have white. And once you encounter the cold gas, so let's say this is the cool gas, teacher, the sun outside got cool gas, got cooler gas, because the outermost part of the cooler outer layers is all relative. So the cooler outer layers will absorb some of the energy, and then some of the wavelengths will be missing. So your absorption spectrum looks like this. That one, rainbow color with lines. So the cold gas steal away some of the lines, steal away some of the lambda. So you get this absorption spectrum. Okay, So what is line emission spectra? When the hot interior of the star sends out white light that passes through the cold gas. Cold gas absorbs energy of a specific wavelength. Then you explained before in quantum physics 1. Absorb energy of photon. So once we absorb the energy of photon, we will have this absorption spectrum. This rainbow color with missing wavelength. That's the first thing. Second idea that we need to talk about is from your AS. Because look, light is a wave. And because it's a wave, it will show the Doppler. The Doppler effect. It's the apparent change in frequency due to relative motion between the source and the observer. You can say it fast in Sheldon's voice. Okay, so this Doppler effect is whenever there's a change in frequency because something is moving. And here is how it looks like. Let's say you have a sun or a star that is moving away from the observer here. Oh, my head, I'm the observer. Okay, so the sun is moving away from me. Oi, sun, where are you going? Sun, hello, come back. Okay, so this sun is moving away from me. And when the sun is moving away from me, the light wave is stretching of light wave. So here, from the perspective of my dude here, lambda increase. Okay, and if let's say, I don't know why, there's another human here, lambda will decrease because as the wave source travel, it will compress the wave. This here is B. So it is the change in frequency or wavelength. If you want to make it specific to star, then it's of the EM radiation due to relative motion between the source and the observer. Source and the observer. Okay, so how that looks like when it comes to us is we can look at the star, and what we will do is we will look at the signature line spectrum. So we feel that if, let's say, this star is at rest, this is what I will see. But I noticed that there is something called a redshift. A redshift is when this wavelength, you can see, right, all the wavelength is like shifted. Everybody is shifted. So or not, everyone is shifted. Just bump. So this means it is receding from us. If it's blue shifted, it means that it is moving towards us. So here is blue shift, not really because all the light is in the blue region, but you can see it move towards the blue. So this blue shifted here simply means move towards blue. Fancy way to say wavelength decrease lah. Okay, and red shifted here means move towards a red. Fancy way of saying wavelength increase. This is red shift. And guess what? When we stare at the stars, it is always red shifted. Almost all. They all be red shifting. All the stars around us are red shifted. Yep. So I'm not going to derive the equation, okay? Because this equation is given to you and you don't need to know the derivation. So in order to finish on time so I can have my dinner, I'll just give you the equation. Okay. So the shift right here is delta. This shift, let's say I measure from here to here. This shift is your change in wavelength. So this part is the change in wavelength. Okay. So the whole ratio here is still the same as your Doppler effect equation. All right. The only difference now is we are doing some approximation. Okay, but at the end of the day, it's still a Doppler effect. When I have time, I will record the derivation. So today we're just going to learn how to use this. And for this one, given now, so we just use that. Let me define all the variables first. So delta lambda here is the change in wavelength. Normally redshift. Change in frequency. Okay. What about lambda and f? Lambda is the wavelength at if the star or the sun or the object is at rest. The rest frame, the original one. Okay. Same thing as f, it will be frequency if the star is at rest. All right. What is v? V here is the speed of the, I want to say the universe expanding, but basically this is the speed of the star. Okay, and this one here is the speed of light. Okay. So we can now relate this to your expansion of the universe or Hubble's law. You imagine there is a Earth observer. Wherever this person look, I look here, I measure a star. I look there, I measure a star. I wait for some season to pass and the Earth to move in the orbit and I measure another star. And I keep measuring and measuring and measuring, and almost all the stars show redshift. Almost all. Almost all, my friend. The spectra of all galaxies, apart from a few that is very near to us, all show redshift. So this means that the galaxies are moving away from us. So then our friend Hubble, the dude who made the microscope, you know him? So our friend Hubble, he went and draw this graph. So he used this graph to estimate the age of the universe. So if we look at this graph, right, on this horizontal axis, you have velocity. And how do we calculate velocity? We use v over c. It's the change in apparent wavelength divided by the wavelength of the source or the star. So we can calculate v. This is v. All right. Is this log scale? Yep, it's log scale. All right. Anyway, doesn't matter. We get a linear graph. And the distance here is megaparsec. Megaparsec is a unit of distance. I don't think it's part of the syllabus. It wasn't specified that you need to know how to convert. And in fact, they did say that Hubble's law is to be used for SI units only. So you just treat it as a unit for distance, but if you need to calculate, it will be in meter. All right. So you notice that there's a trend. It's more like that you get a straight line, best fit line, like this, something like this. Of course, then you'll be wondering, teacher, why the scatter so far away one? This is because of observational uncertainty and random galaxy motion. Because we are limited by how accurate we can measure. And we may not always be able to measure this accurately. But since it's a straight line, we can actually write out the equation that v, which is the y-axis, is approximately equal to h0 times d. X-axis, the distance. So I'll label this one, you need to remember because it's not given. Okay, so v here is what we call the recession velocity. Okay, and how do we find the recession velocity? We use the line spectra plus Doppler. Okay, h0 is known as Hubble's constant. Hubble's constant of proportionality. and h naught is equal to 2.2 times 10 to the power negative 18 second negative 1. You are, as usual, not really expected to memorize constants, okay? But in the event that they want you to do this calculation, the constant should be given to you in the question, because this constant is not given to you in your data page. They are like that one now. Okay, anyway, d here is distance, all right? Distance of the galaxy. So we can use this to double check, because we can use this equation to find the distance of the galaxy. And then we can use this to cross check with standard candles. Remember, we did the standard candle, the C4 variable thing? We can use this to cross check with standard candles. Okay. So from this, we can say that the galaxies are all receding away from Earth with a velocity that is proportional to distance, which means the further away you are from Earth, the faster you are running away from Earth. That means the galaxy is accelerating away from us. The further away the galaxy, the faster they run. So distant galaxies are receding with a velocity proportional to distance. You are further, you run even faster. This shows us that the universe is expanding and give us evidence for Big Bang theory. So they may actually ask you to explain this. And the galaxies are accelerating away. A visual that you can use to help you visualize this expansion is, let's say you have a balloon. Okay, and you go and take a Sharpie and make a bunch of marks on the balloon. And then you blow up the balloon. Big balloon. You notice that all the points will begin to move further from each other. Correct? So the expansion is actually in all directions. Does it mean that the Earth is the center of the universe? No. It just means that everybody is running away from everybody. All the galaxies are accelerating away from all galaxies. So this is Big Bang theory. So if everyone is pushed out, then we can theorize that there should be a point in time where everyone existed together. So at t equal to 0, the universe came into being from an infinitely hot, dense point and has been expanding ever since. All right. So what we know now is, from your line spectrum and Doppler, we can calculate the velocity. And we can actually use standard candles to measure the distance of the galaxy. Using both of these, I get this graph. And I notice the further away the galaxy is, the faster it is running from me. Which means it's like blowing up this balloon. The further away the point is, when you blow some more, it will just push further apart. So then I can assume, if I remove what causes the universe to expand, or I turn back time, everything originates from a single point. But it's called Big Bang theory for a reason. We don't know if it's true. Okay. So finally, we can use this to estimate the age of the universe. Okay. So from here, I know that V, age of universe. So I know that V is equal to h naught d. But also at the same time, speed of light that travels to us, c, is also equal to distance d over time, t. So I can say d is equal to ct. So I'm going to put this inside. V is equal to h naught times c and t. But also at the same time, the fastest possible speed v is equal to c. So we're going to assume that the galaxies that are the furthest away from us is traveling at the speed c. So I can write c is equal to h naught times ct. So speed of light sort of goes away, and then you will get h naught is 1 over t, or rather t is 1 over h naught. And we have the Hubble's constant, 2.2 times 10 to the power negative 18. This will give me 4.55 times 10 to the power of 17. And also at the same time, if I convert this to years, it is 14 times 10 to the power of 9 years. So this is how we got the conclusion that the universe is 14 billion years old. But hey, recently, some scientists are proposing that we change Hubble's constant. This h naught is not really that accurate. They're still in the process of changing it, but until they do, our universe is 14 billion years old. How old are you? 17, teacher. I'm 17. Nice lah, nice. What is 14 billion years? Okay, so this is where the syllabus ends. And before I summarize everything and try a question, I want to talk to you about the extension portion. Basically, what is next? Number one, our universe is expanding. Sure, that means the universe is moving away, but it's also moving away faster and faster. How do I know? Redshift of the galaxies that I look at, especially the type 1a supernova, and the luminosity method. I noticed that the star that I look at after a few decades becomes dimmer. Ooh, that means the star is moving away from me. So, but I have slightly different results in regards to the speed of the universe. Okay, but the second question is, so we are trying to make the data match each other. Okay, and that is a work in progress. So if you go to university and then you do more physics, you may be involved in a research project that collects data from this particular star in this particular galaxy, and then you collaborate with all the other scientists throughout the world and put all your data about stars together to come up with proper data about if the universe is expanding, how fast is it expanding? If it's accelerating, how fast is it accelerating? We don't have enough data. Your turn to do your job. Okay. Number two, what is accelerating the galaxies? There has to be a force, right? If something is accelerating, it is gaining energy. So it feels a bit strange that something is accelerating, but we cannot explain why it's accelerating. Why? And because we cannot explain, we use the term dark energy. Because we are in the dark, we don't know. So here's where scientific knowledge more or less stall. We don't know. So basically we're at the we don't know phase. And this is the nature of doing science. You're at the end of your A2 syllabus, hopefully. So you will notice that there are a lot of things that we are still in a work in progress. We inherit information from our ancestors and from our senior, super senior. We learn and then we improve and make it better. Okay? So in summary, what have we learned so far? Then we'll just do maybe a redshift question and call it a day. Okay, so let's say you are, okay, I'm going to steal this a bit so we can save some time. And again, as usual, this printout will be given to you later. So what have we here? From 25.1 and 25.2, we learn to estimate the distance of the star from the observer by measuring things like radiant flux intensity F, okay, using standard candles to find the luminosity. We also learn to use Wien's displacement law to estimate the surface temperature. And putting L and T together and the Stefan-Boltzmann law, we can use this equation to estimate the size or the radius of the star. So this was where things stopped previously. But now we are observing more stuff. So let's go back. part of this observation of lambda. So on this side of both of this, we go, wow, so bright. And then here, so now we look at power, and then we look at intensity, so bright. And then for wavelength, what do we look at? We look at color. Okay, so color. Actually, not color lah, okay? Wavelength is more than color, but you can see it like color, okay? So from wavelength, we can measure the lambda max to find the temperature. But another thing about wavelength is that we can look at the Doppler redshift. So the universe is consistently expanding away from us. So this delta lambda over lambda naught is equal to delta F over F naught, which is approximately equal to V over C. So it is from this equation where we can find the speed of the receding universe, speed of receding universe or galaxies. And we can marry this with Hubble's law. Of V is approximately H naught D. And how do we find the D? There. Distance of the star from the observer here. Can go back to this one to help us get D. Okay. So this is your Hubble's law. It sort of complements the whole scenario. And this is the entire chapter already. And also just to add on, this Hubble's law and this equation helps us see that the universe is expanding. Expansion of the universe. But we don't know why. And this, I mean, there are a lot of theories, but this theory is, there's no proof yet. And maybe we'll never find that. But this is the entire chapter 25. So we learn how to estimate the distance of the star. We learn how to estimate the radius of the star. And we also learn how to estimate how fast the galaxies are moving away from us. And also use this to estimate the age of the universe. Okay? So this is astrophysics in a nutshell. Cosmology is the very last branch here. Basically, we want to study the why behind. But we don't really know why. There's a bunch of theories, but theories are theories. It remains so until someone can actually put together something that the scientific community can agree with. But that's it. All right, I will go and dig out a question from my collection that we can discuss together. Okay, set to do that. But yeah, that's the summary, my friends. I found some examples. I'm going to just ping pong and use different books. Not sure which book this is. So this one. Yep, this is the Oxford University Press book. Okay. So we're going to look at this, and we're also going to look at this. Then we're going to call it a day. But this is a summary of the entire chapter. And I generally find it helpful for paper 4, especially when physics get tougher, to actually always zoom out to double check to make sure that I know what I'm doing. Because the general theme of this chapter is just how do we measure the distance, how do we measure the size, and eventually, how do we measure the speed of the receding galaxies. That's it. All right, let's look at the first one. A spectral line of the star is found to be displaced from the laboratory value by this much. So this is the lambda when things are not moving. As I call this lambda naught. Okay. And this one is the change in lambda. State whether the star is moving towards or away from the Earth and calculate the speed relative to the Earth. So because of this plus, I can say that since lambda increase, okay, the star is moving away. All right. Calculate the relative speed. Delta lambda over lambda or lambda naught is equal to V over C. So change in wavelength is 0.087 nanometer. And the original value of wavelength is 434 nanometer. We are looking for V, and the speed of light is 3 times 10 to the power of 8. You can find it. That's it. But the equations are not complicated. If you know them, you can use them. I mean, we didn't expect very fast, but then this is also quite fast. 6.0 times 1, 2, 3, 4, 10 to the power of 4 meter per second. It's a fast boy. Okay, it's going to be fast, right? So yeah, find the equation, put the value, done. Okay, next. Wavelength of a spectral line. Too big. Maybe I'll frame this now. A little bit, move this a bit. Okay. So wavelength of the spectral line from a distant galaxy is this one. Okay. So this one is from a star in the galaxy. And then this one is in the lab. The light should be like this. You may be wondering what is going on is because scientists have other ways to determine the composition of the stars. And they actually know what to expect if the star is not moving away. But that part is also not included in your syllabus. But this is lambda. Okay. Calculate the speed of recession and the distance to the galaxy. Okay. All right. A. To find the speed of recession, change in wavelength over wavelength is speed of recession over C. What's the change in wavelength? Minus log, no, minus. 398.6 subtract 393.3. Right? Divide by the original. You be careful, which one is the original? The one in the lab. 393.3. All of this is in nanometer, so it doesn't matter. They'll go away. We're looking for V, and the speed of light is, as usual, 3 times 10 to the power of 8. 398.6 minus 393.3. Okay. I have my V as 4.04. 2715. times 2, 4, 6, 10 to the power of 6 meters per second. It's very fast, okay? But then universe is quite big. Actually, right, when you think about the scale of human and universe, it's just too ridiculous there. It's too ridiculous. It's too hard to fathom how small we all are. Okay. All right. B. Distance to the galaxy. So we're going to use the Hubble equation, H0d. And we got this 4.0 times 10 to the power of 6. We have H0 given now 2.2 times 10 to the power negative 18. Only for D, we find D here. Negative 18. This will give me a distance of 1.837, so 1.84. 1.8 times 10 to the power 24. Okay. So questions are not going to be that hard in this section. Maybe that's why they didn't include any in your syllabus. Okay. They could ask what is the conclusion of this Hubble's law, which is the universe is expanding because everything is redshifted. That's your answer. Okay. Universe is expanding because of the redshift. All right. So that's it for astrophysics. They can pick and choose some. Some of the equations are linked mainly by luminosity and distance from the observer. All right. So today we have speed run the entire chapter. How is your brain? How's my brain? I don't know. Let me look at the chat. Are you okay? Am I okay? I think I did okay. Finish now. Okay, finish now. It's Malaysian way of saying it is done. So learn to map out everything that you learn and see how they are related. Because at the end of the day, when we look at the star, we go like, oh, it's so bright. So we measure the intensity of the light that arrives at the planet or on Earth, and also how the intensity change over time, so that we can actually reliably know L. And once we know L, which is luminosity, the power of the sun or the star, we can estimate how far away the star is from us. And once we can estimate how far away the star is from us, we can use the Stefan-Boltzmann law together with Wien's displacement law to find the size of the star. So then we can come up with things like, oh, Proxima Centauri is 2 times the size of this star. Like, how do you know? Here's how we know. Wien's displacement law just says that we are looking at black body radiation. Anything that emits heat will emit electromagnetic radiation. So color, not color lah, the brightness. So that Wien's displacement law will help us decide, because we can measure the wavelength, what the temperature is, and then we can use the Stefan-Boltzmann law, this one, to find the radius of the star. Okay, and finally, cosmology section, we are going to look at the Doppler redshift. We notice that everything that we look, no matter when, no matter how, most of the galaxies is redshifted. It means everyone is running away from us. Doesn't that feel very lonely? Okay, so it means that the entire universe is expanding. We can tell this from our friend Hubble's law. They use Hubble's law. And besides explaining clearly how the universe is expanding, or why the universe is expanding, mainly it is because of this redshift. Because we know it is redshifted, so we can say everything is running away from us, so universe is expanding. And we can plug into Hubble's law to estimate the distance of the universe. And also using redshift to find velocity. Okay. Let's look at the chat. Does that mean the distance between the sun and other planets keep increasing? Yes. The distance between all celestial objects keep increasing over time. Okay. Thank you, Jude. All the best with your teaching as well. And thanks, Dylan. And also for those of you who reply and kept me company. I remember you. All right. So all the best for your papers and what you're doing. We're all in a pandemic now. The world is a strange place, but also the world is a good place. So be good to people around you. Be good to yourself. All the best. I'll see you. I don't know when. Bye-bye. Whoever is watching this video, whenever you watch this. Cheers. Link to this, I'll throw it in the chat. I'll throw it in the comment section later. Okay, take care, guys. From Malaysia to you. Bye-bye.